Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route towards sleep. Tonight we're wandering into a question that sounds simple at first, and then becomes wonderfully stubborn the longer you sit with it. How cold can anything really get? And why is there a final limit that nature refuses to let us touch? Somewhere out there in textbooks, laboratories, and the back of many winter-themed conversations, there is a number that gets treated almost like the basement of reality itself. Absolute zero. The coldest possible temperature, a point so low that it sounds less like weather and more like the universe muttering, "No, that is far enough." Before we ease into it, I would love to know where you are listening from tonight, or this morning, or perhaps in that strange in-between hour when the room is dark but your mind is still doing its own small orbit. What time is it where you are? Is it warm where you're sitting, or have you wrapped yourself in a blanket and decided that learning about impossible cold is best done while remaining safely above freezing? There is something a little amusing about that, really. Humans do seem to enjoy studying dangerous extremes from very comfortable positions. We like volcano documentaries from the sofa. We like black hole videos while sipping tea. And apparently we also like the coldest concept in physics while remaining politely attached to central heating. If you find this kind of slow unfolding science soothing, or interesting, or just a pleasant way to quiet the noise of the day, do consider liking the video and subscribing. It helps this calm little corner of the internet reach more people who might enjoy a softer kind of curiosity. And if the thought of the coldest possible temperature sounds like an odd companion for sleep, I understand completely. But I promise this is less about shivering and more about the rules of the universe, and those can be surprisingly comforting once they begin to make sense. Now then, let us start with the phrase itself, because absolute zero has the kind of name that sounds very sure of itself. It does not sound negotiable. It does not sound like something with an almost or a maybe around the edges. It sounds final. It sounds like the last stair in a staircase, the bottom drawer in a cabinet, the point beyond which there is simply nowhere left to go. And in one sense that is true. Absolute zero is the lowest temperature allowed by the laws of physics. In Fahrenheit it sits at minus 459.67 degrees. In the Kelvin scale, the scale physicists prefer, when they want temperature to start from a meaningful physical flaw, it is simply zero. Not chilly, not very cold, not colder than Antarctica, not colder than a dark winter night on some lonely mountain. It is the limit. And yet, for all how definite that sounds, the truly strange part of the story is not that this lower limit exists. The strange part is that we can get closer and closer to it with extraordinary cleverness and still never quite arrive. Not because we are sloppy, not because our tools are crude, not because scientists have somehow forgotten to bring an extra blanket. We cannot reach it because the closer we get, the more nature changes the rules of the chase. The final distance does not behave like an ordinary distance. It behaves like one of those maddening tasks that gets harder precisely because you are succeeding. This is one of the reasons absolute zero has such a grip on the imagination. It is not just cold. It is unreachable cold. It is a destination written on the map with no road that actually ends there. You can spend a lifetime building better machines, better methods, better laboratories, and you can still only approach it the way one approaches the horizon. You move toward it, and it remains ahead. That may sound like one of those grand dramatic statements science writers sometimes make when they are trying to add mystery to something that is mostly just equipment and measurements. But in this case, the mystery is real. The story of absolute zero is the story of humans learning that temperature is not simply a matter of hot and cold in the ordinary everyday sense. It is a story about motion, energy, order, disorder, quantum behavior, and the stubborn refusal of matter to become perfectly still. The deeper you go into it, the less it resembles ordinary experience. You begin with ice and winter and breath in the air. You end with lasers, magnetic traps, ultra-high vacuum chambers, and atoms behaving in ways that would make no sense at the scale of soup, sweaters, or afternoon weather forecasts. Still, that is getting ahead of ourselves slightly, and there is no need to rush. One of the pleasures of a topic like this is that it begins in familiar territory. Everyone knows what it means to feel cold. We know the practical version of it. Cold pavement through thin shoes, cold hands searching for a mug, cold air meeting your face when you step outside and instantly regret your optimism about the season. We also know that cold seems like the opposite of heat, in the straightforward way that silence seems like the opposite of sound. Less heat, more cold, simple enough. But physics has a habit of taking everyday impressions and asking a more precise question beneath them. What is cold exactly? That is where the flaw begins to shift. Because in everyday life, we tend to treat cold as though it were its own substance, its own thing, almost as if heat can be added and cold can be poured in afterward, like some opposite ingredient. But that is not really how nature works. There is energy involved, motion involved, and when something gets colder, what is really changing is not that it is filling up with some special essence of coldness. It is that the microscopic ingredients inside it are carrying less thermal energy. Their jostling, vibrating, colliding behavior is reduced. The restless internal activity becomes less restless. Already, you can begin to feel why absolute zero would be special. If temperature is tied to motion at the microscopic level, then lowering temperature is, in some sense, reducing motion. Not motion in the simple sense that the whole object slides across the table. A brick can sit perfectly still and still be warm. What matters is the hidden activity inside it. Molecules vibrating, atoms bumping and twisting, tiny ceaseless motion everywhere. To cool something is to drain away some of that activity. And if you keep draining it away, you are led naturally to a provocative thought. Could you remove all of it? Could you calm matter down completely? Could you persuade every atom and molecule into perfect stillness? Could nature, under ideal circumstances, become utterly motionless at the smallest scale? That is the dream implied by the phrase absolute zero. Not just very little motion, but none at all. A final quiet, a complete stop. If you picture it too literally, it almost sounds peaceful. The universe, holding its breath. But this is also the point where physics begins to look back at us and say gently but firmly that our intuition is trying a little too hard. Because nature does not actually let matter settle into the kind of perfect stillness our common sense would like to imagine. Long before we get to the full explanation, it is worth noticing how often this happens in science. We make a concept from ordinary life, stretch it into the microscopic world, and discover that the universe has signed only part of the agreement. It allows an approximation, not the final version. Yes, things can be made colder. Yes, internal motion can be reduced. Yes, extraordinary states of matter appear when we do that. But the final, absolute, the perfect total stillness stays out of reach. There is also something a little humbling about the fact that absolute zero is not merely difficult in the way climbing a tall mountain is difficult. Mountains can be climbed if you have the skill, the preparation of the oxygen, and perhaps a very strong sense of determination. Absolute zero is difficult in a deeper way. It is forbidden as an achievement. The closer you get, the more expensive each tiny improvement becomes in effort and ingenuity. You do not simply need better gloves, you need better understanding, better isolation, better control over light, magnetism, pressure, and the environment surrounding the particles you're trying to cool. You begin to realize that cold is not a substance you can pile up. It is a condition you have to coax out of matter by carefully removing energy without accidentally adding any back in. That last part turns out to be maddeningly important. In the ordinary world, almost everything is constantly exchanging energy with everything else. The room warms the cup warms your hand, the air warms the metal, the floor cools your feet, radiation arrives, vibrations spread, molecules collide, heat leaks in from every direction like gossip in a small town. To get something extremely cold, you must isolate it from all those exchanges, and the colder it gets, the more sensitive the whole setup becomes. A tiny intrusion that would mean almost nothing at everyday temperatures can matter enormously near the bottom of the scale. So there is the practical challenge, which is already serious enough. But then there is the deeper challenge, and this is where the story becomes unmistakably physical, rather than merely technical. Even if you had a perfect laboratory, perfect insulation, perfect patience, and all the intelligence modern science can bring to bear, there remains a law-like barrier. Reaching absolute zero would require a kind of final extraction of thermal energy that cannot be completed in a finite series of steps. Every real process leaves some remainder. Every approach has a limit. Every path toward perfect cold narrows into impossibility. Now, if that sounds discouraging, I would offer a gentler way to look at it. Science is full of unreachable points that still teach us extraordinary things. You do not have to stand on the horizon to learn from walking west. You do not need to touch a star to understand stellar physics. And in much the same way, getting close to absolute zero has transformed modern science, even though the final destination remains withheld. Some of the strangest and most beautiful behaviours in matter only appear when temperatures become unimaginably low. Materials begin to conduct electricity without resistance. Fluids climb walls and flow without friction. Atoms can gather into shared quantum states that look less like ordinary particles and more like one unified wave of behaviour. Entire branches of modern physics have opened up not because we conquered absolute zero, but because we learned how to approach it with enough finesse to see what lies near the edge. There is a nice irony in that. The impossible limit has turned out to be one of the most productive ideas in laboratory science. It is a wall that behaves more like a doorway. The closer researchers come, the more surprising the landscape becomes. And perhaps that is part of the reason the subject remains so compelling. It is not merely about a number on a scale. It is about what happens when the ordinary thermal blur of the world begins to fade, and the quieter, stranger rules underneath start to show themselves. At this point, you might reasonably ask whether absolute zero is just one of those neat theoretical limits that mathematicians and physicists enjoy, but that reality never really notices. In other words, does it matter that it cannot be reached if no one was ever going to get there anyway? The answer is very much yes. The fact that it cannot be reached is not a trivia note. It is woven into thermodynamics, into the behaviour of entropy, into the structure of quantum mechanics, and into the way real cooling methods work. The impossibility is not an afterthought, it is the point. But before we get into laws with grand names and experimental methods involving more ingenuity than seems fair for one species, it helps to stay for a moment with the most basic picture. Imagine any ordinary object around you. A mug, a pillow, a window latch. To your eyes it looks calm and solid, but at the microscopic level it is busy. The atoms inside are not frozen in the everyday sense of the word. They vibrate around positions, interacting with their neighbours, sharing energy in a constant hidden bustle. Even a block of ice, which we think of as a symbol of stillness, is not truly still inside. Its particles have motion, its structure has activity. Temperature is one way of describing that hidden busyness, so cooling is not adding cold. Cooling is reducing busyness, and the closer you try to get to total calm, the more you discover that total calm is not the kind of thing nature hands out. There is something almost philosophical about that, though physics itself keeps it refreshingly concrete. Perfect rest turns out to be a suspiciously classical dream. Matter at very low temperatures does not simply become a quieter version of its ordinary self. It begins to act in ways that reveal the quantum grain of reality. And quantum rules, unlike our common sense, do not allow us to specify everything with unlimited precision and then demand complete stillness on top of it. There is always some irreducible remainder, some minimum restless character that cannot be bullied out of existence. The universe, at its deepest level, is not built for perfect mechanical silence. Even so, Scientists are a stubborn and inventive group, and it would be wrong to imagine they heard this and simply folded their arms. Quite the opposite. They learned how to cool gases by letting them expand, how to use evaporation in controlled ways, how to exploit magnetic properties, and eventually how to use laser light itself to slow atoms down, which still sounds like a trick until you realise it is a Nobel Prize-winning one. They built refrigerators far stranger than the one humming in your kitchen. They created techniques that would have sounded like fantasy a century earlier, and by doing so they discovered that near absolute zero, matter does not become dull. It becomes revealing. That is why the question of why absolute zero can never be reached is more than a technical curiosity. It is really a doorway into what temperature means, what heat is, how energy moves, why entropy matters, and where classical intuition gives way to quantum behaviour. The impossibility at the end of the journey forces us to understand the journey itself, and that, conveniently enough for us, is exactly where the story wants to go next. Because to see why the final step can never be taken, we first need to get clear on what temperature is actually measuring in the first place, and why what feels like warmth and cold to us is underneath. A very busy microscopic conversation that never becomes quite as silent as we imagine. So let us begin there with a word so familiar that most of us hardly notice how much meaning we have quietly packed inside it. Temperature. We check it before getting dressed. We complain about it in winter and misjudge it in spring. We set it on ovens, air conditioners, kettles, baths, and far too optimistically on thermostats, just before realising the room still feels exactly the same. Seems obvious at first. Hot things have a high temperature, cold things have a low temperature. End of story. But physics, being physics, hears that and gently says not quite. Because temperature is not just a label for how warm or cold something feels to your skin. In fact, your skin can be wonderfully dramatic and not always especially reliable. A metal chair in a cool room can feel much colder than a wooden one sitting right beside it, even when both are at the same temperature. A tiled floor can seem almost hostile first thing in the morning, while a rug feels forgiving, though the room itself has not secretly divided into competing climates overnight. Your body is judging how quickly heat moves into or out of you, and from that it creates an impression. Very useful in daily life. Not quite the same thing as the underlying physics. So what is temperature really measuring? At the microscopic level, matter is busy. Not metaphorically busy, literally busy. The atoms and molecules inside every object around you are in motion. In a gas, they fly around, colliding, rebounding, changing direction like tiny, over-enthusiastic commuters who have all lost the map. In a liquid, they slide past one another, still moving, still interacting, but with less freedom than in a gas. In a solid, they are more constrained, usually vibrating around fairly fixed positions, which sounds calm until you remember that there are astonishing numbers of them doing this all at once. A table may look still. A block of ice may look calm. A spoon on the kitchen counter may appear to have achieved perfect emotional stability. But on the inside, their particles are not just sitting there doing nothing. Temperature is one way of describing how energetic that microscopic motion is. That sentence sounds neat and tidy, but it helps to linger with it for a moment. Because this is the point where the familiar everyday word starts to become more precise. When physicists talk about temperature, they are talking about the average energy associated with the random motion of particles in a substance, not the overall movement of the object through space. A train can race down the tracks while remaining cold. A rock can sit perfectly still in the sun and become warm. What matters is the internal motion, the restless microscopic jostling within the material itself. This is why heating something up is not magic, even if it occasionally feels that way when toast appears. When energy is added to a substance, the particles inside it usually move more vigorously. Their collisions become more energetic, their vibrations become stronger, their random motion increases, the temperature rises. When energy is removed, those same particles settle into less energetic motion, and the temperature falls. That is the basic picture. not warmth as a mysterious essence, not cold as some invisible fluid being poured in, just particles with more or less internal kinetic activity. Now the word average matters quite a lot here. If you could somehow shrink yourself down to the scale of molecules, which I do not recommend as a long-term lifestyle choice, you would not find every particle moving in perfect lockstep at exactly the same speed. That would be far too organised for the real world. Some particles would be moving faster than others, some slower, some would be colliding at one moment and drifting more gently the next. Temperature is not a statement about one particular particle. It is a statement about the overall distribution of their random motion. It tells you, in a broad statistical sense, how much microscopic agitation is present. That last point is one of the quiet surprises of thermodynamics. So much of heat and temperature turns out to be statistical. We do not follow every particle individually, because there are far too many. Even in something as ordinary as a breath of air or a sip of tea, the number of molecules involved is beyond anything your intuition can hold comfortably. So physics steps back and asks a larger question. Given this vast swarm of particles, what can we say about the average behaviour? Temperature is one of the answers. This also explains something that often confuses people at first. Temperature is not the same thing as total heat content. Those sound similar in casual conversation, but they are not identical. A tiny spark can be much hotter than a bathtub full of warm water, yet the bathtub contains far more total thermal energy overall, because there is so much more stuff in it. In the same way, a small cup of boiling water has a higher temperature than a swimming pool on a mild summer afternoon, but the pool contains vastly more total energy simply because of its size. So temperature is not a measure of how much energy an entire object has in total. It is more about how concentrated that thermal motion is on average at the particle level. That difference matters because it helps prevent one of the most common mental mix-ups. We often imagine a hot object as one that simply has more heat in it. Sometimes that is loosely fine in everyday life, but when precision matters, temperature tells you about the average microscopic energy, while the total thermal energy depends both on temperature and on how much material there is, and also on what kind of material it is. A thimble of boiling water and a bathtub of warm water are not thermally interchangeable, no matter what the thermometer says, and your bath routine should remain mercifully aware of that. Another useful way to approach this is through equilibrium, which sounds like the sort of word that belongs in a lecture hall but is actually describing something very common. Put a hot mug of tea on a table and leave it alone. Over time it cools. Leave a cold glass of water in a warm room and it warms up. In both cases, energy moves around until the objects and their surroundings come to the same temperature. That shared temperature is what we call thermal equilibrium. When two systems are at the same temperature, there is no net flow of thermal energy between them. There may still be microscopic collisions and exchanges, of course. Nature never stops fussing entirely. But on average, there is no overall trend in one direction. The jostling balances out. That simple fact is part of why temperature is such a useful concept. It acts like a kind of negotiator between objects. If one thing has a higher temperature than another, energy tends to flow from the hotter one to the colder one until balance is reached. Your coffee cools because the room is cooler. Ice melts in your drink because the drink is warmer. Your hands warm a cold mug if the mug begins colder than your skin. Temperature tells us which way that exchange tends to go. Still, to really get comfortable with what temperature measures, it helps to look at different states of matter, because the microscopic picture is not quite the same in all of them. In a gas, particles are relatively far apart and move around freely. Their temperature is closely connected to how energetically they zip about and collide. The hotter the gas, the faster, on average, those particles move. This is why heating a gas tends to make it expand if it is free to do so. The particles strike the boundaries of their container more vigorously, or spread farther apart when not confined. A warm balloon behaves differently from a cold one, not because it has developed opinions, but because the particles inside it are moving with more energy. In a liquid, things are a little less tidy from the point of view of simple explanation, though very interesting from the point of view of physics. The particles are closer together, interacting more strongly, and constantly rearranging around one another. They still move randomly, still carry thermal energy, but now that energy is shared among different kinds of motion and interaction. Molecules can translate, rotate, vibrate, and tug against neighbouring molecules. So when we say temperature measures average kinetic energy, that basic idea remains true, but real substances can distribute energy in more complicated ways than the neat first picture suggests. Nature has a habit of letting the textbook in through the front door, and then quietly adding rooms at the back. Solids are different again. In many solids, the atoms are not travelling across the object the way gas particles move through a room. Instead, they vibrate around equilibrium positions in a lattice or structure. Increase the temperature and those vibrations grow stronger. Decrease it, and they become weaker. A hot metal rod, a warm stone, a cool pane of glass, all of them contain particles vibrating with different average energies. The object itself appears solid and fixed, yet internally it is full of motion. This is one reason temperature can feel almost counterintuitive. The things that seem most still are, at a microscopic level, never fully still. Now, because temperature is tied to microscopic motion, it is tempting to imagine that two objects at the same temperature must somehow have particles moving in exactly the same way. But not at all. Different materials respond differently because their atoms and molecules have different masses, structures, and ways of storing energy. A piece of iron and a cup of water can sit side by side at the same temperature, yet the details of their internal motion are not identical. Their particles differ, their bonding differs, their capacity to absorb energy differs. This is why different materials heat up and cool down at different rates. Water, in particular, is famous for requiring a relatively large amount of energy to change its temperature, which is one reason oceans have such a stabilizing effect on climate, and why a cup of tea can remain annoyingly too hot for longer than your optimism predicted. Thermometers, then, are not detecting some mystical property called hotness. They're responding to physical changes that correlate reliably with temperature. In an old-style liquid thermometer, the liquid expands when warmed and contracts when cooled. In a digital thermometer, electronic properties change in measurable ways. In very precise scientific instruments, temperature can be inferred from radiation, resistance, magnetic behavior, or other effects. But in every case, the goal is the same: to quantify the microscopic agitation of matter in a way that gives us a consistent scale. And scales, of course, are where human culture enters and makes things slightly more confusing than strictly necessary. Celsius, Fahrenheit, Kelvin. Each has its own history, its own logic, and occasionally its own ability to start family arguments about what counts as mild weather. But the important point for now is that these scales are ways of assigning numbers to the same underlying physical reality. The number itself is not the temperature in some deep cosmic sense. It is a human convention laid on top of a measurable phenomenon. What matters physically is the state of the particles, the internal energy distribution, the tendency of heat to flow. The scale is our bookkeeping system. This becomes especially important when people say something like cold does not really exist, only the absence of heat. That statement is trying to get at something real, but like many clever statements, it needs a bit of unpacking before it behaves itself. Cold is certainly a meaningful experience. Your skin would be delighted to confirm that. But in physics, we generally describe what is happening in terms of lower thermal energy, rather than some separate substance called coldness. We add energy to warm things, we remove energy to cool them. We talk about temperature decreasing, not about cold being poured in from a hose. So while cold exists perfectly well as a human description, the underlying mechanism is about how much microscopic motion remains. That is also why the idea of a lower limit to temperature begins to make sense. If temperature is tied to random microscopic motion, then lowering temperature means reducing that motion. The natural question becomes whether there is a flaw. Can the motion be reduced without end, or is there some final point beyond which it cannot go? We are not answering that fully just yet, but you can already see why the question arises. Once temperature is no longer just a number on a weather app and instead becomes a measure of microscopic activity, the dream of perfect cold turns into the dream of perfect stillness, and that is a much stranger thing to ask of nature. Before we drift there though, one more distinction is worth keeping in view, because it sharpens the whole discussion. Temperature measures the tendency of energy to spread through microscopic motion, but it does not tell you everything about an object all by itself. Two objects at the same temperature can feel different, behave differently, contain different total amounts of energy, and respond differently when heated further. Temperature is powerful, but it is not the whole thermal story. It is one very important window into the collective motion of matter, not the entire house. That can sound frustrating at first, as if physics keeps handing you one clear idea and then surrounding it with careful exceptions. But this is actually part of what makes the subject so satisfying. Temperature begins as a sensation, becomes a measurement, then deepens into a statistical description of particles in motion. What felt like a basic household concept turns out to be one of the main bridges between our human scale and the invisible microscopic world. It connects weather reports to molecular collisions, boiling kettles to atomic vibrations, fever thermometers to statistical mechanics. It is both ordinary and profound, which is a rather nice combination if you think about it. And perhaps the most comforting part of all this is that the world remains familiar even after the explanation becomes deeper. Tea still cools, ice still melts, blankets still help. Metal doorknobs still feel far ruder in winter than they really need to. The science does not replace the experience, it simply reveals the machinery beneath it. What feels like warmth is a flow of energy. What feels like chill is a greater drain of it. What a thermometer reads is the average behaviour of countless particles engaged in their ceaseless small motions. So when we ask what temperature really measures, the answer is not warmth in the poetic sense, nor comfort, nor the mood of the air, nor how strongly your body objects to getting out of bed on a January morning. It measures the average microscopic thermal motion inside matter. It is a way of taking the hidden busyness of atoms and molecules and giving it a number. And once you start seeing temperature that way, you are already standing at the edge of the next idea, because those atoms and molecules are not merely abstract particles in a definition. They are moving, colliding, vibrating, tugging, and rearranging in patterns that make the entire thermal world possible. And to understand why cooling matter becomes harder the closer we push it toward complete quiet, we need to stay with them a little longer and watch that tiny restless dance more closely. If temperature is a way of describing microscopic motion, then the next thing we need to do is slow down our own thinking enough to picture that motion properly, because it is very easy to say that atoms and molecules are always moving and then immediately imagine something far too simple. We picture tiny balls bouncing around like cartoon marbles. We imagine a miniature version of the visible world, only smaller, a little mechanical drama taking place beneath the surface of everything. That picture is not entirely wrong, which is often the most dangerous kind of wrong. It gives us a foothold, but it also hides how strange the real story is. Because atoms do move, and molecules do move, and all matter around us is alive with motion at scales too small to see. But this motion is not always the same kind. It is not one single dance repeated everywhere. It changes with temperature. It changes with the state of matter. It changes with how strongly particles are bound to one another, how much space they have, how much energy they are carrying, and what quantum rules are quietly organising the performance behind the curtain. Still, there is a good reason people start with the image of a dance. A dance suggests pattern and freedom at the same time. It suggests motion that is not random in every possible sense, but not rigid either. It allows for structure, collisions, hesitation, rhythm, and changing relationships. If you try to imagine matter at the microscopic level as perfectly fixed, you will miss almost everything important. If you imagine it as complete chaos with no form at all, you will miss almost everything important again. The truth sits in the middle. Matter is restless, but that restlessness is shaped. Take a single breath of air around you. It feels calm enough. The room does not seem particularly dramatic. Nothing in the air is announcing itself with any great urgency, unless perhaps someone nearby has burned toast. But on the microscopic level, the particles in that breath are in constant motion. They are darting through space, colliding with one another, rebounding, shifting direction, exchanging energy. They do not politely line up and move in agreement. They swarm, they scatter, they cross paths and part. There are enormous numbers of them doing this all the time, so many that the air seems smooth and steady to us. But smoothness at our scale is often just wild activity averaged out. That hidden activity is one reason gases behave the way they do. A gas fills its container because its particles are free to move through the available space. They keep flying until something stops them, usually another particle or the wall of the container. Pressure, at its heart, comes from these countless impacts. Warm the gas and the particles move more energetically on average. Cool it and they move less energetically on average. Already you can see the connection to temperature again. The hotter the gas, the more vigorous the dance. The colder the gas, the gentler it becomes. But even in a gas where the motion is easiest to imagine, we should be careful. Not every particle moves at the same speed. Some race along faster, some drift more slowly. Their energies are spread across a range. Temperature does not tell us that every particle has identical motion. It tells us something statistical about the whole crowd. The dance floor is not synchronized, it is populated. Now compare that to a liquid. A liquid is also in motion at the microscopic level, but its dance is more crowded. The particles are much closer together. They cannot simply roam through large empty distances the way gas particles can. They jostle, pull on one another, slip past one another, and remain in near constant contact. This is why a liquid flows yet keeps a relatively fixed volume. Its particles are mobile but not free in the same way. There is a kind of compromise between movement and togetherness. That compromise gives liquids their distinctive feel in physics. Pour water from a glass and it changes shape instantly, adapting to its container, but it does not expand to fill the entire room. Its molecules are moving and rearranging, yet they are also linked by interactions strong enough to keep them close, raise the temperature, and those molecules move more energetically, making the liquid easier to evaporate and often less viscous. Lower the temperature and the motion becomes less energetic. The fluid thickens in many substances. At the right conditions, it may freeze into a more ordered structure. Through all of this, the dance continues. It simply changes style. Solids are perhaps the most misleading of all from the perspective of everyday intuition, because a solid appears still. A chair seems still. A stone seems still. A steel railing in winter seems still in the deeply unwelcoming way only winter steel can manage. Yet the atoms inside a solid are not motionless. In many solids they are arranged in repeating structures, each atom bound near a particular position. But bound near a position does not mean frozen in place like a photograph. It means vibrating. They tremble around those positions, tugging against the forces that hold the structure together, constantly moving within limits. So even the most apparently motionless object in your room is hosting a hidden choreography. Each atom vibrates. Each bond flexes. Energy moves through the structure as collective vibrations ripple across many atoms at once. That matters enormously for heat flow. When one part of a solid is warmer, the atoms there vibrate more strongly, and that disturbance can pass along to neighbouring atoms. In this sense, thermal motion is not merely individual, it can become collective. A warm metal spoon placed in hot soup does not become hot by magic. The energy spreads through the metal because microscopic motion and interaction transmit it. This is where the phrase slow dance begins to earn its keep. At low temperatures, the dance does not stop, but it changes character. The amplitudes of vibrations become smaller, the average motion becomes less energetic, collisions become gentler, rearrangements become rarer, but there remains motion, there remains activity. The particles do not simply receive a memo announcing that the performance is cancelled. They persist, though in quieter form, and the quieter the dance becomes, the more our ordinary imagination starts to fail us. At room temperature, it is still fairly natural to talk in terms of particles moving around. At very low temperatures, especially in carefully controlled systems, the motion begins to reveal features that are not well described by everyday pictures. The particles still have energy, but the way they carry it and share it becomes increasingly shaped by quantum rules. Their behaviour begins to depend not only on simple jostling, but on allowed states, collective effects and limitations that have no direct parallel in daily experience. Before we go fully there though, it helps to sit for a moment with just how deeply motion is built into matter. This is not some occasional property that appears only when we heat things dramatically. It is the default condition of the material world. A tabletop is not still in the absolute sense. A block of ice is not still in the absolute sense. A sleeping cat looks wonderfully still and dignified, at least when not dreaming, but on the molecular scale there is thermal motion everywhere inside that cat, inside the cushion, inside the air around the whiskers, inside the whole domestic scene. Temperature is not added to matter as an afterthought. Thermal motion is part of what matter is like under ordinary conditions. This becomes easier to appreciate if you think about how much of the visible world depends on those hidden motions. Smells spread through a room because molecules move and mix. Sugar dissolves in tea because molecules interact and rearrange. Ice melts because the motions in the crystal structure change enough for the rigid arrangement to break down. Steam rises because water molecules in the gas phase move freely and disperse. Brownian motion, that gentle jitter of tiny particles suspended in fluid, is the visible trace of invisible collisions. Again and again, the stillness of the world at our scale is revealed to be an illusion of scale, a summary rather than a literal truth. Even biological life depends on this microscopic dance, the chemistry inside cells, the folding of proteins, the movement of molecules across membranes, the functioning of enzymes. All of it relies on thermal motion. Life is not separate from the dance, it is built within it. Warmth is not just comfort, it is activity. Too little and many processes slow dramatically or stop functioning in the usual ways. Too much and structures break down. Organisms exist within a narrow and very particular thermal window, because the dance of atoms and molecules has to be lively enough for chemistry, but not so violent that the delicate organisation of life comes apart. This gives temperature a slightly more intimate meaning. It is not just a number outside us. It is a description of the microscopic tempo that much of ordinary reality depends on. There is something almost reassuring in that once you get used to it. The world is not a collection of dead static objects waiting to be nudged into action. It is already active, already moving, already exchanging energy and rearranging itself in tiny ways too numerous to count. At the same time, physics asks us to resist turning this into romance. The motion is not there to look beautiful for us. It is simply what matter does under the laws that govern it. The elegance comes later in our understanding. Nature is not performing a ballet for our benefit, it is following rules, but the result, when seen clearly, is no less remarkable for that. Now, if all matter contains this ceaseless microscopic motion, then cooling something means reducing the energy in that motion. In a gas, that may mean slowing the particles on average. In a solid, it may mean reducing vibrational activity. In a liquid, it may mean calming the constant rearrangement and agitation among neighbouring molecules. The details differ, but the broad idea holds. Cooler means quieter, hotter means livelier. So why can we not just continue reducing the dance until it disappears entirely? Part of the answer is practical. Any attempt to cool a system requires removing energy, and that is harder than it sounds when everything is connected to everything else. The environment leaks energy in. Containers interact with contents. Radiation arrives. Even measuring a system can disturb it. The microscopic dance is not happening in isolation unless we work very hard to isolate it, and the colder the system becomes, the more significant every small disturbance can be. But the deeper answer has to do with the nature of the dance itself. At low enough temperatures, atoms and molecules do not merely become slower versions of their warmer selves. The available ways they can move become restricted by quantum mechanics. Energy is not always smoothly adjustable in the way classical intuition expects. Certain vibrational modes and states matter. Entire collections of particles can begin to behave coherently. What looked like a swarm of individual dancers can start to act more like a coordinated ensemble. This is one of the most striking things about the low-temperature world. As thermal agitation fades, subtler forms of order become visible. At ordinary temperatures, so much microscopic motion is present that many delicate quantum effects are washed out. It is like trying to hear a whisper in a crowded station. Lower the temperature enough and some of that crowd noise disappears. Suddenly behaviours that were always allowed but usually hidden come forward. Superconductivity, superfluidity, strange magnetic ordering, condensates of ultra-cold atoms. Near the coldest conditions we can make, matter reveals traits it normally keeps buried under thermal commotion. That means the slow dance of atoms is not simply a lesser version of the fast dance, it becomes qualitatively different. There is less random agitation, yes, but there can also be more collective structure. Less noise can mean more pattern. The world does not merely go dim, in some ways it becomes clearer. You can think of it as the difference between a crowded room where everyone is talking at once and a quiet hall where a few distinct voices can finally be heard. At higher temperatures, many microscopic possibilities are excited. Energy is distributed widely across them. At very low temperatures, fewer possibilities remain significantly occupied, and the underlying structure of matter begins to stand out in sharper form. That is why low-temperature physics is not just the study of cold things, it is the study of what matter does when thermal distraction is minimized. Even so, minimized is not the same as abolished. That is the crucial point. However slowly the dance proceeds, however quiet it becomes, physics does not permit us to demand that every last trace vanish in the classical sense. The particles cannot all be pinned down into perfect stillness with perfect certainty. There remains a baseline unease in nature, a minimum residual character to motion and energy that cannot simply be negotiated away. To understand why, it helps to notice that position and motion are not, in the quantum world, quantities we can specify with unlimited sharpness at the same time and then calmly declare finished. A particle confined to a region cannot also possess perfectly definite zero motion in the ordinary classical way. The very structure of quantum theory resists that demand. Bound systems retain ground state energy. Vibrations do not fade all the way to nothing in the simplistic sense our intuition would like. Matter refuses to settle into the perfectly silent statue we imagine. This is why the phrase absolute zero can mislead when heard too casually. It suggests complete emptiness of motion, complete stillness, a final pause. But the microscopic reality is subtler. As we approach the lowest possible temperature, what we are really doing is stripping away thermal excitations, reducing random energy, and pressing matter toward its lowest accessible states. Those states are astonishingly quiet compared with ordinary life, but not classical stillness. The dance has not ended. It has become the minimum dance allowed, and that minimum is not just a technicality, it is the reason the final approach to absolute zero becomes impossible. You can remove more and more thermal energy, you can slow the dancers, you can dim the noise, isolate the stage, and use every brilliant trick modern experimental physics has devised. But the last demand, the demand for perfect silence, is not compatible with the rules of the theatre. All of this makes the ordinary world feel slightly different once you have seen it. A glass of water is no longer merely a passive object. It is a moving assembly. A pane of metal is a vibrating structure. Air is a storm of molecular collisions that only looks calm because you are made of the same kind of large-scale averaging as everything else. Warmth becomes visible as increased microscopic restlessness. Cold becomes a decrease in that restlessness. And the path toward deep cold becomes a gradual calming of the ceaseless internal dance that defines matter itself. That is why this topic has such a peculiar charm. It starts with something as basic as feeling cold, then leads us to a world where all matter is motion, where stillness is partly an illusion, and where the closer we get to quiet, the more fundamental the remaining motion becomes. The dance slows, it does not vanish. And once that is clear, the next part of the story almost introduces itself, because humans, being who we are, did not stop at understanding that heat is motion. We immediately began trying to remove it. We built methods, machines, and entire scientific traditions around the idea of taking energy away as carefully as possible, learning step by step how to chase colder and colder conditions without ever quite reaching the final hush. Once people began to understand that heat was not some invisible fluid of comfort, but a real physical form of energy moving through matter, the hunt for cold changed from a seasonal inconvenience into a scientific pursuit. Before that, most of human history treated cold as something you found rather than something you made. Winter brought it, mountains stored it, deep caves borrowed it, night offered a little of it back after a punishing day. If you wanted something cold, your best strategy for a very long time was simply to be patient, move somewhere inconvenient, or know a person with access to a large hole full of ice. That may sound almost charming now, in a world where chilled drinks arrive with offensive confidence, and freezers hum away in kitchens as if they invented the concept personally, but it really was a remarkable limitation. Human beings have always needed ways to preserve food, cool bodies, store medicines, and survive heat. Yet for thousands of years, the coldest technologies available were mostly architectural and agricultural. People harvested winter ice from lakes and rivers, packed it in sawdust or straw, and stored it in insulated pits or special buildings. Wealthy households and entire cities built ice houses. Snow was collected from mountains and carried down to settlements. In some cultures, frozen or semi-frozen treats were made by mixing snow with fruit or flavourings, which is a wonderfully human response to natural hardship. Faced with a harsh winter landscape, someone eventually said yes, but what if dessert? Even earlier than that, there were clever tricks that did not require frozen weather at all. One of the oldest and most elegant is evaporative cooling. If you leave water in a porous clay container, a small amount of the water seeps to the surface and evaporates. The molecules that escape into the air carry away energy, leaving the remaining water cooler. The effect is not dramatic enough to turn a summer field into the Arctic, but it works. It can make stored water noticeably cooler than the surrounding air, especially in hot, dry climates. It is a very ancient piece of thermal wisdom. Long before anyone could explain kinetic energy or molecular escape, people learned by experience that nature would cool things for you if you let the right molecules leave first. That little principle, which seems so modest at first, turns out to be one of the key ideas in the entire history of refrigeration. To cool what remains, let the most energetic particles escape. It works when sweat evaporates from skin. It works in clay vessels. It works in much more sophisticated laboratory systems many centuries later. And there is something satisfying about that continuity. Some of the most advanced cooling methods in physics are, at heart, still playing variations on lessons people once learned from water jars and hot afternoons. For a long time, though, these methods belonged more to craft and practical living than to science. Cold was useful, but it was not yet fully understood. Heat itself was only gradually becoming a subject of systematic study. People knew that fire warmed, ice cooled, and some materials seemed better at storing or transferring warmth than others, but the deeper question of what heat actually was took centuries to settle. Was it a substance, a fluid, a quality, a motion? Scientists argued, Experiments accumulated. Language lagged behind. The world kept boiling kettles and freezing ponds while human thought tried to catch up. One older theory imagined heat as a subtle fluid, sometimes called caloric. This idea had a certain intuitive appeal. Heat seemed to flow from hot objects to cold ones, so why not treat it as a kind of invisible stuff? It explained some observations reasonably well, or at least well enough to survive for a while, which is often the fate of an idea that is not quite right but not immediately embarrassing. But over time, experiments showed that heat behaved less like a conserved fluid and more like something bound up with motion and energy. Friction could generate it. Compression could affect it. Mechanical work could produce thermal effects. The deeper scientists looked, the less heat resembled a ghostly liquid, and the more it resembled organized disorder at the microscopic level. That shift in understanding was crucial, because once heat became something you could remove, transfer, or transform as energy, refrigeration stopped being a matter of lucky weather and became a matter of engineering. Cold no longer had to be found. It could be produced indirectly by taking heat away. The first real steps toward artificial refrigeration were not especially glamorous. They often involved laboratories, pumps, strange chemicals, and more patience than any sensible dinner guest would tolerate. In the 18th century, experimenters began showing that liquids can cool when they evaporate rapidly under reduced pressure. Lower the pressure, encourage evaporation, and the remaining liquid gets colder. This was a scientific version of the old claypot lesson, only more controlled. One early demonstration used ether, a liquid happy to evaporate quickly, and showed that artificial cooling was possible. It did not immediately lead to every home owning an icebox, but it proved an important point. Nature did not reserve cold for mountain tops and winter storms. With the right conditions, a human-built system could create it. That realization opened the door to one of the most important habits in science, the refusal to stop once something is shown to be possible. Once people saw that heat could be removed by clever manipulation of pressure and phase changes, they began improving the methods. Vapors could be compressed, liquids could be allowed to expand, fluids could circulate, heat could be drawn from one place and dumped into another. Refrigeration, in the modern sense, is not really about creating cold as if from nowhere. It is about moving heat against the direction it would naturally prefer to go. Left on its own, heat spreads out. Refrigeration says yes, but not today, and then spends energy forcing the heat elsewhere. That is what a refrigerator in your kitchen is doing, despite its calm domestic exterior. It is not generating a magical pocket of coldness. It is pumping heat from the inside of the box to the room outside. The food feels cool because thermal energy has been removed from it and expelled into the surrounding space. In a lovely piece of household irony, the back of a refrigerator is warm precisely because the inside is cool. The machine is doing thermal bookkeeping. It steals heat from your leftovers and pays the bill by dumping that heat into your kitchen, plus a little extra from the electrical work required to run the system. So the refrigerator is not defeating thermodynamics. It is cooperating with it in a slightly smug and rectangular way. The development of that technology took time. In the 19th century, inventors refined vapor compression systems, in which a refrigerant is compressed until it heats up, then cooled so it condenses, then allowed to expand and evaporate again, absorbing heat as it does so. The details became more practical, more reliable, and more suited to large-scale use. Industrial refrigeration changed food storage, shipping, brewing, meat packing, medicine, and daily life. Suddenly, cities were less dependent on the local season. Perishable goods could travel farther. Ice could be manufactured. Climate itself, at least in small enclosed spaces, began to feel negotiable. There is something quietly revolutionary about that. A civilization that can control temperature gains a new kind of freedom. It can preserve food across distance and time. It can store medicines safely. It can make hospitals more effective. It can build chemical industries that depend on controlled cooling. It can create comfort in hot regions and precision in laboratories. Refrigeration is one of those technologies so woven into modern life that its absence is hard to imagine. Yet its fundamental achievement is still the old one. Remove heat, redirect energy, encourage matter to settle into a less agitated state than it would choose on its own. As the technology improved, so did ambition. It was one thing to cool food or produce ice. It was another to ask how cold matter could be made in principle. That is where engineering began to merge with deep physics. Scientists became interested not just in practical refrigeration, but in extreme refrigeration. What happens to gases if you cool them enough? Can all gases be liquefied? Can liquids become solids under the right conditions? What are the limits? These questions pushed the field toward cryogenics, the science of very low temperatures, where cold stops being merely convenient and becomes revealing. This was not a simple progression. For a while, some gases were thought to be impossible to liquefy because they resisted the methods available. That resistance turned out not to mean they were fundamentally immune, but that the techniques and pressures required were more demanding than anyone had yet mastered. As scientists improved their ability to compress, cool, and expand gases in controlled stages, more and more of these stubborn substances yielded. Air could be liquefied. Oxygen and nitrogen could be liquefied. Hydrogen eventually followed under more extreme conditions. Each success was not just a technical milestone, it was a lesson in how energy, pressure, and phase changes cooperate. One of the central tricks here is that when a gas expands under the right circumstances, its temperature can drop. This is not a universal fairy tale where every expansion leads to cooling no matter what, but under many practical cryogenic conditions it becomes a powerful tool. Compress a gas, let it release heat, then allow it to expand. Repeat in stages. Use the cooling from one stage to help the next. Build cascades. Recover losses. Insulate everything. Progress comes, but slowly, because the closer you move toward the low temperature frontier, the more demanding every leak, every impurity, every stray source of warmth becomes. That creeping difficulty shaped the culture of low-temperature physics. It made the field both ingenious and slightly obsessive, which may be the only sensible response when the environment is constantly trying to ruin your experiment by being warmer than you asked it to be. A warm room becomes the enemy. A support bracket can conduct too much heat. Radiation from surrounding surfaces matters. Air itself becomes a nuisance. The coldest systems must be protected from nearly everything that would be harmless in ordinary life. It is a bit like trying to preserve a whisper in the middle of a busy train station. You do not merely need a quieter speaker, you need isolation from the whole surrounding riot. Researchers learned to use vacuum chambers to reduce heat transfer by air. They built double-walled vessels with reflective surfaces to limit thermal radiation. They invented specialized containers to hold liquefied gases without immediately squandering them to the surroundings. They discovered that every degree of cooling bought with great effort could be lost again by carelessness in material choice or geometry. Cold, at extreme levels, is less like a possession and more like a negotiation. You must defend it constantly. Along the way, people also learned that some of the most effective routes to deeper cold involve phase changes and selective escape. Evaporative cooling appears again in refined form. If the most energetic particles in a liquid or trapped gas are allowed to leave, the remaining particles have lower average energy, so the temperature drops. The same broad principle that cools sweat on skin becomes, in controlled settings, a serious scientific method. Nature, even when pushed into elegant laboratory arrangements, still favours the same basic logic. Remove the energetic few, and the average quiets. Then came one of the most delightful twists in the whole story, the realization that light itself could be used to cool atoms. On first hearing, this sounds exactly backward. Light warms things. Sunlight warms stones. Lamplight warms your desk. Anyone who has stood too near stage lights or old bulbs knows that illumination and heat have long maintained an annoyingly close relationship. So the idea of using laser light to make atoms colder has the quality of a physics punchline. And yet it works, because what matters is not our everyday impression of light, but the momentum carried by photons and how atoms respond to carefully tuned beams. By arranging laser light in clever ways, scientists can preferentially oppose the motion of atoms, nudging them into slower states. Add magnetic fields and additional trapping methods, and suddenly it becomes possible to cool dilute gases to temperatures that would have seemed fantastical to earlier generations. At these scales, the word cooling no longer means anything like placing a drink on ice. It means reducing the motion of individual atoms with exquisite control. The chase has become microscopic in the most literal sense. Humans are no longer merely building colder cellars. They are persuading atoms to move less. There is a lovely continuity here between the oldest and newest methods. The ancient world used shade, wind, night, and porous clay. The industrial world used compression, evaporation, and expansion cycles. The modern laboratory uses magnetic fields, vacuum, ultra-clean environments, and laser light. Yet all of them are expressions of the same broad ambition: move heat away, reduce agitation, quiet the microscopic dance. What changed over time was the level of understanding and the level of control. Early humans knew that ice preserved fish better than warm air, but they did not need a molecular theory to profit from that fact. Later inventors knew that vapor compression could manufacture cold at scale, even before the deepest microscopic explanation was complete. Modern physicists, by contrast, often begin with the theory and then build machines precise enough to exploit it. The path from ice houses to atomic cooling is not merely a story of better tools, it is a story of better questions. What is heat? How is it stored? How is it transferred? What is temperature measuring? What happens if we strip away more and more thermal motion? At what point do ordinary materials begin revealing extraordinary behaviour? And that last question is really what pushes the history of refrigeration into the history of fundamental physics. Because once cooling became good enough, scientists stopped asking only how to keep things cold and began asking what cold does to reality. Some materials lose electrical resistance. Some fluids flow without viscosity. Some gases condense into collective quantum states. Magnetism changes. Chemistry changes. Matter stops behaving like a slightly quieter version of its room temperature self and starts behaving like something that had been waiting all along for thermal noise to die down enough for its stranger habits to show. That makes the human pursuit of cold feel almost philosophical, though in practice it was often driven by very practical needs and stubborn experimentation. We wanted safer food, better storage, relief from heat, and control over industrial processes. We got all of that. But we also got a deeper encounter with the laws of nature. The more successfully we removed heat, the more clearly we discovered that there are rules governing how far that removal can go. By this point in the story, it becomes impossible not to notice a change in the meaning of the word zero. In everyday life, zero on a temperature scale can just mean some arbitrary point chosen by convention. One more line on a thermometer, useful perhaps, but not profound. But as humans learned to chase colder and colder states, it became clear that there might be a kind of true lower boundary, not just a mark chosen by habit, but a meaningful physical flaw. A temperature so low that it is not merely another step down from winter, but the point where the very idea of thermal motion reaches its deepest limit. And before we can understand why that flaw can never actually be reached, we need to pause at the scale that was built to make that flaw visible at all, because zero there is not just a number. It is the place where the entire hunt for cold changes its meaning. There is something very human about the number zero. We like to imagine it as a clean line, a point of nothing, a place where the count begins and perhaps where confusion ends. 0 apples means no apples. 0 messages can feel either peaceful or deeply suspicious depending on the day. 0 on a game scoreboard means no one has managed anything yet. It feels simple. It feels definite. And because it feels definite, we tend to carry that same instinct into temperature. We assume 0 degrees must mean the same sort of thing, a natural baseline, a beginning, perhaps the point where cold finally becomes serious and everyone starts dressing with better judgment. But temperature scales do not all use 0 in the same way, and this is where the Kelvin scale becomes quietly fascinating. On some scales, 0 is a human choice. On the Kelvin scale, 0 is not just a convenient place to start drawing the ruler. It is meant to represent a real physical boundary, the lower limit of thermal temperature itself. That is a very different kind of 0. To see why this matters, it helps to remember that temperature scales are inventions. The world did not come with little numbers printed along the side of reality. Human beings built scales so that thermal conditions could be measured consistently, shared, compared, and eventually understood. That seems obvious, once said, but it matters because whenever humans invent a scale, we have to choose a starting point. We have to decide what counts as 0, what counts as one step upward, and how those steps will be defined. Sometimes those choices are practical rather than profound. On the Celsius scale, for example, 0 was tied to the freezing point of water under familiar conditions, and 100 was tied to the boiling point. That is a very useful choice for everyday life, especially if your species cooks, drinks tea, and remains strongly invested in whether puddles are about to become hazardous. Water matters to us, so a scale built around water is convenient. But there is nothing in the deep structure of the universe that says the freezing point of water must be the fundamental beginning of temperature. It is important to us, not to nature as a whole. The Fahrenheit scale is even more obviously historical in its personality. It emerged from a set of practical reference points that made sense within a certain era and context, even if later generations have occasionally looked at it with the bemused expression usually reserved for antique medical advice. Again, there is nothing wrong with that. A scale can be useful without being fundamental. But it means the 0 point on Fahrenheit is not a cosmic flaw. It is a choice. Kelvin is different. The Kelvin scale was designed to strip away some of that historical accident and anchor temperature to the physics itself, instead of asking where water freezes or what a convenient laboratory reference might be. It asks a more basic question. If temperature measures thermal motion, or more broadly the thermal energy associated with microscopic agitation, what would the lower limit of that quantity be? Where does the scale naturally bottom out if we stop thinking like weather watchers and start thinking like thermodynamics? The answer is absolute 0. Not just a cold benchmark, not just a memorable line on the thermometer, but the point at which thermal temperature reaches its minimum possible value. That is why 0 on the Kelvin scale is so strange compared with other zeros. It is not arbitrary. It is aspirational and physical at the same time. It says here is the floor, even if you can never actually stand on it. That already makes Kelvin feel less like a household scale and more like a map of the underlying machinery of matter. 0 Kelvin does not mean water freezes. It does not mean winter. It does not mean unpleasant metal benches. It means the lowest limit of thermal energy in the sense captured by thermodynamics. It is the point toward which all cooling aims and beyond which ordinary temperature simply does not extend downward. Now, that sounds clear enough, but the moment you say it out loud, a new confusion tends to arrive. If 0 Kelvin is the lowest possible temperature, does that mean everything stops? Does it mean absolutely no motion? Does it mean all energy is gone? Does it mean matter has become some kind of perfect silent statue? This is where the meaning of 0 becomes even stranger, because the answer is not as simple as our everyday instincts want it to be. When people hear 0, they often hear nothing. But 0 Kelvin is not the same as nothing at all. It does not mean no matter. It does not mean no structure. It does not even mean no energy in the broadest imaginable sense. A system at its lowest possible thermal state can still possess what quantum physics forces it to retain. Bound particles can still have ground state energy. Atoms in a solid can still exhibit residual motion of a quantum sort. The system is not empty, it is not erased, it is simply at the lowest thermal condition allowed. That is one reason this zero has such an unusual feel. It is both absolute and subtle. It is absolute in the sense that there is no lower ordinary thermodynamic temperature beneath it. But it is subtle because it does not correspond to the common language idea of perfect nothingness. It is a limit on thermal behaviour, not a universal cancellation of all existence. You still have matter, you still have quantum rules, you still have reality behaving according to its laws. What you do not have is any room left to lower the thermal temperature further in the usual sense. There is also a conceptual elegance to the Kelvin scale that becomes easier to appreciate once you notice another feature. The size of 1 Kelvin step is the same as the size of 1 Celsius degree. The difference is not in the spacing, the difference is in where 0 is placed. In everyday terms, moving upward by 1 Kelvin means the same size change in temperature as moving upward by 1 degree Celsius. The scales climb with the same stride, but they begin in different places. Celsius begins at a convenient water-based landmark. Kelvin begins at the deepest lower bound. That means converting from one to the other is mostly a matter of shifting the origin rather than changing the size of the steps. And there is something telling about that. It reminds us that measuring is partly about the scale and partly about the reference point. Change where you call 0, and the entire emotional feel of a number changes. A room that sounds pleasantly positive in Celsius becomes a much larger number in Kelvin, even though nothing physical has changed. The particles do not care what names we give the marks on the ruler. They keep moving exactly as they were. Still, our choice of ruler matters for understanding. Kelvin is the preferred scale in much of physics because it aligns directly with fundamental thermal ideas. Equations become cleaner. Relationships become more transparent. Most importantly for our story, the meaning of 0 becomes physically honest. There is no pretending that 0 is just the weather getting nippy. 0! Kelvin says we're talking about the endpoint, the place where the classical dream of removing all thermal agitation runs out of road. Historically, this was a profound shift. It took temperature from the level of practical measurement into the level of principle. The Kelvin scale emerged from the work of scientists who were trying to understand heat not merely as a sensation or a laboratory quantity, but as something tied to energy, work, and the laws governing physical systems. The scale is named after William Thomson, later known as Lord Kelvin, who recognised that thermodynamics points naturally toward a lower limit. He was not inventing a dramatic-sounding 0 for the sake of tidy bookkeeping. He was following the logic of heat engines and energy flow toward a scale whose 0 had real physical meaning. And this is where 0 on Kelvin starts to feel almost philosophical, though it remains stubbornly practical. Many zeros in human life are accounting choices. 0 on a bank balance means you have reached a reference point our financial system cares about. 0 on a road sign may simply mark the start of a route. 0 on a clock can reset after a cycle. But 0 Kelvin is different. It is not the beginning of our record. It is the lower edge of the phenomenon itself, at least as far as ordinary thermal temperature goes. It is not just where we started counting, it is where nature says there is nowhere lower to count in that direction. That physical seriousness changes the whole emotional shape of the scale. On Celsius and Fahrenheit, 0 can be crossed with no great metaphysical drama. Temperatures can go below 0 because those scales are anchored to everyday reference points rather than ultimate limits. Winter does not care where humans decided to place the mark. The atmosphere will proceed as it pleases, but on Kelvin, 0 is not casually crossed. Under ordinary thermodynamic conditions, it is the boundary. Negative values on that scale are not part of ordinary cooling. For most purposes, the scale begins there and only goes upward. Now, there is a niche and very interesting wrinkle involving exotic systems sometimes described as having negative absolute temperatures, but these are not colder than 0 Kelvin in the intuitive sense. In fact, they behave in ways that make them effectively hotter than arbitrarily high positive temperatures. Since our story tonight is about the ordinary meaning of absolute zero as the lower thermal limit, it is wiser not to get lost in that side corridor. It is a fascinating corridor, but it tends to steal the furniture from the main room. What matters here is that for ordinary systems and ordinary thermodynamics, Kelvin zero is the floor. Even so, calling it the floor can be a little misleading if it makes you imagine a solid surface you could eventually step onto with enough determination. It is more like a boundary that gives structure to the whole temperature scale while withholding itself from direct arrival. The Kelvin scale is built around a destination that real processes can approach, but not complete. That makes 0 Kelvin unlike the zero on almost any ruler you have used in ordinary life. On a normal ruler, if you keep moving left, you reach the edge and there it is. On the Kelvin scale, the edge exists as a physical limit, but the act of reaching it turns out to be forbidden. This gives the scale a curious dual role. It is both a measuring tool and a statement about the universe. Every temperature written in Kelvin quietly carries the implication that the count began at the deepest possible cold. A gas at a few hundred Kelvin is not just warm by some convention. It is that many increments above the absolute lower bound. A cryogenic experiment at a tiny fraction of a Kelvin is operating astonishingly close to the floor, though never on it. The scale lets physicists see immediately how near or far a system is from the coldest limit nature allows. That is especially useful because our ordinary temperature language becomes less helpful the deeper we go. Everyday speech is built for weather, fever, comfort, and cooking. It is not built for comparing the inside of a room with an ultra-cold atomic trap in a high vacuum chamber. Kelvin gives a scale that remains meaningful all the way down. It lets the low-temperature world be described without the clutter of arbitrary reference points borrowed from water and human climate habits. And yet, for all its usefulness, the strange thing is that Kelvin zero remains partly a conceptual horizon. We define it. We build scales from it. We understand its significance. We approach it in experiments. But we do not settle into it as an achieved condition. That makes it a rare kind of zero, both measurable and unreachable, both exact in theory and evasive in practice. There is something almost paradoxical in that. We often think a number is most meaningful when it points to something easy to identify. 0 apples, 0 chairs, 0 unread messages if the day is going suspiciously well. But 0 Kelvin is meaningful precisely because it identifies a limit that cannot be completed by finite means. Its reality is not diminished by that. In fact, the impossibility makes it more revealing. It tells us something deep about thermodynamics. It tells us that the thermal world is not infinitely reducible by ordinary operations. There is a bottom, but it is not a resting place we can casually occupy. This is also why the Kelvin scale helps discipline the imagination. Without it, it is tempting to think of colder and colder conditions as just more of the same, as if you could descend forever like a miner in an endless shaft, always going lower if only you had the stamina. Kelvin reminds us that no, the shaft has a bottom. The cold cannot decrease without limit. There is a final boundary even if the last step remains untaken. And perhaps the strangest part of all is that a scale built around absolute zero ends up teaching us not about stillness, but about what remains when stillness is denied. Near the bottom of the Kelvin scale, quantum effects become impossible to ignore. Matter behaves collectively. Superconductivity and superfluidity appear. Atomic gases condense into unusual shared states. The lower the thermal noise, the more clearly these underlying patterns emerge. So the scale that begins at the imagined end of motion becomes the scale through which we discover some of the most intricate motion and organization matter can display. That is a very physics sort of joke, really. We go searching for nothing left to happen, and instead we find new things happening that were hidden all along. So when we speak of the strange meaning of zero on the Kelvin scale, we are really speaking about a number that is not merely a number. It is a physical boundary disguised as the start of a ruler. It is the point where arbitrary temperature conventions give way to thermodynamic structure. It is the lower limit of thermal temperature, not because humans voted for it, but because the laws of nature force the scale to bottom out there. And unlike the other zeros we use in daily life, this one does not mean a simple absence. It means the lowest reachable meaning of thermal quiet, though never the completed possession of perfect silence. Once that is clear, the next difficulty almost introduces itself. If the Kelvin scale starts at a true physical floor, and if experiments can move closer and closer to that floor, then why does the last distance become so stubborn? Why does every improvement demand more effort than the last? Why does the approach slow into something like a law of diminishing returns written into nature itself? To answer that, we need to look at what happens when cooling stops being just a matter of going lower and starts becoming a matter of chasing an ever more expensive final fraction of a degree. At first glance, cooling something seems like it should be one of the simpler jobs in physics. If heat is energy, then remove the energy. If the particles are moving too much, slow them down. If the object is too warm, expose it to something colder. This is the kind of problem that sounds almost practical enough to solve with a determined expression and a very large freezer. And for a while, that impression seems to hold. Bringing a hot object down to room temperature is usually easy. Cooling room temperature matter to the temperature of ice is also familiar enough. Going lower than that takes more planning, but it is still within the range of ordinary technology. The real surprise comes later, when each further drop becomes more difficult than the last, and the final approach toward absolute zero turns into one of the most demanding pursuits in all of experimental science. This change in difficulty is not an accident of poor engineering. It is not because scientists suddenly become clumsy when they are already tired from all the cooling. It is built into the way heat, energy transfer, and matter behave. The closer you get to the bottom of the temperature scale, the less nature cooperates with the idea of taking one more clean step downward. Methods that work beautifully at higher temperatures become inefficient. Sources of unwanted heating that once seemed trivial become serious obstacles. The amount of thermal energy left to remove becomes smaller, yet somehow the challenge does not become smaller with it. Quite the opposite, it becomes more exacting, more delicate, and more unforgiving. One way to begin seeing why is to think about how cooling works in the first place. Heat usually flows from warmer things to colder things. That is the natural direction. Put a warm drink in a cool room and energy leaves the drink. Put ice in a warmer liquid and energy flows into the ice. The bigger the temperature difference, the stronger the tendency for heat to move. This means that when an object is much warmer than its surroundings, cooling it is relatively easy. Nature is willing to help. The gradient is large. There is a strong imbalance. Energy flows readily. But as the temperature difference shrinks, that easy help starts to fade. If an object is only slightly warmer than its environment, the rate of heat flow drops. The push is weaker. Cooling becomes slower. This is true in everyday life. A very hot cup of tea cools quickly at first, and then lingers in that mildly warm state for an annoyingly long time. Anyone who has waited for a drink to become just right has already met this principle in domestic form. The first part is dramatic. The last part tests your patience. Now extend that idea into low-temperature physics. If you are trying to cool matter far below room temperature, you need an environment colder still, or a method that effectively removes energetic particles or thermal energy by some controlled process. But each time you lower the temperature, the next stage demands an even colder sink or a more refined mechanism. The closer you get to 0 Kelvin, the fewer natural places there are to dump heat. There is no convenient colder room waiting for you. There is no ordinary winter night ready to do the work. You have to build each stage of the descent yourself, and each stage becomes harder because the available thermal margin gets smaller. That is only the beginning. Another difficulty comes from the fact that the remaining heat becomes harder to separate cleanly from the system. At higher temperatures, matter contains plenty of thermal energy spread across many motions and modes. Remove some, and the temperature falls in a robust, noticeable way. At very low temperatures, the amount of thermal energy left is already small. That may sound encouraging, but it also means that any stray input from the environment, becomes proportionally more important. A tiny leak that would be meaningless at room temperature can ruin an ultra-cold experiment. A little vibration, a little radiation, a little imperfect insulation, a little energy from the measuring apparatus itself, all of these become serious. It helps to picture the problem in plain terms. Imagine trying to cool a metal object sitting on a kitchen counter. The room is warm, the counter conducts heat, the air transfers heat. Light from surrounding surfaces carries heat as thermal radiation. Touch it with your hand and you warm it. In ordinary life, none of this matters very much because everything is already operating within a broad, comfortable temperature range. But in a low-temperature laboratory, every one of those pathways becomes an enemy. Researchers have to fight heat entering through solid supports, through residual gas molecules, through electromagnetic radiation, and even through the wires used to monitor the system. The colder the target becomes, the more absurdly careful the setup must be. This is one reason low-temperature apparatus often looks less like a simple machine and more like a defensive strategy. Layers of insulation, vacuum spaces, reflective shields, special materials, multiple cooling stages, suspended structures designed to limit conduction, filters and traps to keep outside disturbances from sneaking in. The goal is not merely to cool the sample, it is to prevent the entire rest of the universe from politely undoing your work. And the universe is very good at undoing your work. Heat is not something that sits still when ignored. It spreads, it leaks, it arrives through channels you forgot to worry about. At room temperature, we get away with a lot because the stakes are low. Near absolute zero, the stakes are microscopic but severe. It is a world in which a tiny imperfection becomes the whole story. There is also a more subtle problem. Many cooling methods rely on extracting the most energetic particles or excitations from a system. This works because once those energetic members leave, the average energy of what remains drops. Evaporative cooling is the standard everyday version. The fastest water molecules escape from sweat or from a porous clay vessel, and what remains becomes cooler. Laboratory cooling often uses analogous ideas in much more controlled ways. But as the temperature falls, the population of very energetic particles shrinks. There are fewer easy targets to remove. The system becomes harder to cool by the same method because the tail of the energy distribution is no longer so generous. That means a technique that works efficiently early on begins to lose its bite later. You can think of it as picking the low-hanging fruit and then discovering that the tree has become unreasonably tall. At first, there are many particles carrying enough extra energy to be selectively removed. Later, there are fewer. The gain per attempt decreases. More effort buys less cooling. Efficiency slips just as ambition rises. The same pattern appears in refrigeration cycles more broadly. In many systems, you can cool by compression and expansion, by phase changes, by magnetic effects, or by laser-based techniques. But each method has an operating range in which it works best. To get lower, you often need to stack techniques. One stage pre-cools for the next. Liquid nitrogen may help you reach the range where liquid helium becomes useful. Helium-based systems may then bring you down far enough for dilution refrigeration, or magnetic cooling methods to take over. Laser cooling may slow atoms dramatically, but then evaporative cooling may still be required to go lower. It is not one long smooth slide downward. It is a relay race in which every method hands the problem to a stranger. That handoff matters because no single technique remains strong all the way down. Each one runs into limits, and those limits are not merely engineering annoyances. They reflect the fact that different physical processes dominate at different temperatures. What matters in a gas at a few hundred Kelvin is not the same as what matters in an ultra-cold atomic cloud or an electronic system deep in the millikelvin range. As the thermal background shrinks, new forms of coupling and new bottlenecks emerge. For example, at sufficiently low temperatures, the heat capacity of many systems changes. Heat capacity tells us how much energy must be removed to lower the temperature by a certain amount. In some materials and regimes, the heat capacity becomes very small at low temperatures, which sounds useful because it suggests a small amount of energy removal could change the temperature a lot. But this does not magically solve the problem. The small heat capacity also means the system is more vulnerable to tiny unwanted heat inputs. It becomes thermally delicate. A minute disturbance can raise the temperature significantly, so the same feature that makes the system responsive also makes it fragile. Then there is the issue of time. Very low temperature systems often take a long time to settle. Energy may not redistribute instantly within the material. Different parts of the apparatus can end up at different effective temperatures if they are not well coupled. Electrons may cool differently from the lattice of the solid around them. A trapped gas may need time to rethermalize after energetic particles are removed. The thermometer may not perfectly represent the actual temperature of the part you care about. In ordinary conditions, we assume things come to equilibrium in a straightforward way. Near absolute zero, even equilibrium can become an achievement. This leads to one of the stranger features of the subject. Sometimes the act of observing the system becomes part of the problem. To measure temperature, you need interaction. But interaction often means energy exchange. A thermometer touches the system, or radiation is emitted and detected, or electrical properties are probed. Each of these can disturb the very state you are trying to preserve. This is not merely a philosophical nuisance, it is practical. At ultra-low temperatures, the power dissipated by a measurement current or the energy carried by probing radiation can be enough to warm the sample. So even asking how cold something is must be done carefully, with the scientific equivalent of trying not to wake a sleeping cat by stepping around the floorboards one by one. Another reason each step gets harder is that the remaining motion in the system becomes less and less classical in character. At higher temperatures, the thermal behavior of matter can often be understood in fairly direct statistical terms. There is lots of agitation. Many states are populated. Everything is noisy enough that ordinary approximations work rather well. As the temperature drops, however, quantum effects stop being a small correction and start becoming the main story. The system settles toward low energy states, but those states are governed by quantum rules. You cannot demand that every degree of freedom behave like a classical bead rolling to a complete stop. This is where the dream of simple stillness begins to fail. In the classical imagination, cooling is like calming a crowd until eventually no one moves. But quantum systems do not allow that exact picture. Bound particles can retain ground state energy. Modes of vibration do not necessarily vanish into perfect absence. The system can approach its lowest allowed state, but that state is not the same thing as the everyday idea of utter rest. So every step downward becomes harder, partly because what you are chasing is not just less motion, but the selective removal of thermal excitations while respecting the structure of allowed quantum states. You're not sweeping away ordinary disorder from a floor. You are navigating a highly constrained landscape. Thermodynamics adds another layer. The closer you get to absolute zero, the harder it becomes to remove entropy from the system. Entropy is one of those words that people enjoy turning into dramatic statements. But here we can keep it simple. It has to do with how energy and states are distributed, and with how much hidden multiplicity the system has in its microscopic arrangements. Cooling generally means reducing thermal disorder and steering the system toward lower energy configurations. But doing that near the bottom of the temperature scale becomes increasingly demanding. Real processes are not perfectly reversible. Real operations create some entropy of their own. To reach absolute zero would require an ideal level of control and reversibility that physical processes cannot deliver in a finite sequence. This is one of the deep reasons behind the unattainability of absolute zero. It is not just that the refrigerator gets tired, it is that every actual cooling step has limits. To get closer, you need more stages, more care, more time, and more nearly perfect control. The amount of extra cooling gained from each effort shrinks. Nature does not present a final barrier like a wall you can hit once and declare found. Instead, it presents an endless tightening of requirements. Every further reduction becomes possible only through greater refinement, and the full completion of the journey recedes. There is a practical analogy here that stays close to real experience. Cleaning a muddy boot is easy at first. The big clumps come off immediately. Rinsing helps. A brush helps. Soon the boot looks almost clean. Then you notice the thin film left in the seams, the grit in the stitching, the dirt trapped in the tread. Getting from very dirty to mostly clean is quick. Getting from mostly clean to perfectly spotless is much slower and may never really happen outside a showroom. Low temperature physics has something of that pattern, except the consequences are more serious and the dirt is made of unwanted energy, entering through every available loophole. And yet, scientists keep going lower. That is worth pausing over because the increasing difficulty is not the same as futility. Over the past century, researchers have driven temperatures down by astonishing amounts, reaching millionths and even billionths of a Kelvin above absolute zero in carefully prepared systems. The progress is real. The methods are ingenious. Laser cooling, evaporative cooling, dilution refrigerators, adiabatic demagnetization, ultra-high vacuum techniques, exquisitely sensitive isolation schemes, all of these have pushed the frontier lower and lower. The point is not that cooling becomes impossible early on. The point is that every new level of cold comes at a steeper price in complexity and control. That rising price also reflects specialization. Near room temperature, a household refrigerator can cool food without needing to know anything about quantum states or magnetic entropy. Near absolute zero, the system often has to be tailored to the specific material or particles involved. Cooling atoms in a trap is different from cooling electrons in a nanostructure. Cooling a bulk material is different from cooling a thin film. Some degrees of freedom may cool efficiently while others lag behind. Some interactions help, others spoil the result. The universal household simplicity disappears, replaced by a world in which everything depends on exactly what is being cooled and how it is coupled to the apparatus. There is even a psychological trap in the language. Because we say colder and colder, it sounds as though the scale were uniform in difficulty, as though each step down were like descending equal stairs. But that is not what the physical landscape feels like at all. The numbers may be evenly spaced on the Kelvin scale, yet the effort required to traverse those intervals is not evenly spaced in any practical sense. Dropping from room temperature to a cryogenic temperature is a major achievement. Dropping another small fraction when you're already deep in the millikelvin regime can be a challenge of an entirely different order. The ruler is linear, the struggle is not. This mismatch between numerical simplicity and physical difficulty is part of what makes absolute zero so unintuitive. We see a scale and imagine a path. Physics gives us a scale and then tells us the terrain becomes worse the lower we go. At first the road is broad, then it becomes narrow, then it becomes icy in the way only physics can manage, with the added inconvenience that the word icy has ceased to mean what it usually means. So every step toward absolute zero gets harder because the natural flow of heat weakens, because environmental leaks matter more, because standard cooling methods lose efficiency, because different degrees of freedom stop cooperating equally, because measurement itself becomes intrusive, because quantum constraints take over, and because thermodynamics refuses to allow a finite procedure to complete the job. The closer you get, the more the universe asks of you. Better isolation, better timing, better control, better understanding, less noise, less carelessness, less of everything really except patience. And patience in this field is not just a virtue, it is infrastructure. Experiments may run for long periods to settle into the desired state. Cooling stages must be executed carefully. Apparatus must be prepared with extreme cleanliness and precision. Researchers learn to think in leaks, couplings, stray photons, vibration paths, and hidden heat loads. The achievement is not merely lowering a number, it is building a temporary pocket of reality in which nearly every ordinary source of thermal mischief has been suppressed enough for matter to become quieter than it ever is in daily life. That is the remarkable thing. The reason every step gets harder is the same reason the whole subject becomes more revealing. At ordinary temperatures, thermal motion hides many delicate behaviours. Lower the temperature and those behaviours begin to emerge. But to uncover them, you must first overcome nature's deep resistance to perfect cooling. Difficulty and discovery rise together. The challenge is not separate from the science, it is the science. And once that pattern is clear, the next question becomes unavoidable. If the increasing difficulty is not just practical but structural, then what exactly is nature resisting? Why does the thermal world refuse the final descent? What principle lies underneath this mounting stubbornness? To answer that properly, we have to turn to the idea that sits quietly behind so much of thermodynamics, because the closer we move towards perfect cold, the more we run into the problem of order, disorder, and the strange persistence of entropy. To understand why nature resists the final push toward absolute zero, we have to spend some time with a word that has earned a slightly intimidating reputation. Entropy. It is one of those scientific terms that people like to borrow for dramatic effect. A messy desk becomes entropy. A difficult week becomes entropy. A drawer full of tangled cables becomes, quite unfairly, the second law of thermodynamics apparently made visible. But in physics, entropy is not just a fancy word for chaos. It is a way of describing how energy is distributed and how many microscopic arrangements are available to a system while still looking the same from the outside. That sounds technical, and it is, but the basic idea is not out of reach. In fact, once you begin to see it, a great deal of the thermal world starts to make more sense. Imagine a room full of people just after a concert ends. At first, everyone is packed into one area, focused on the stage, facing roughly the same direction, sharing the same event. Then the lights come up, people start moving, some head for the doors, some stop to talk, some realise they have lost a scarf, some take the long route for no clear reason at all. After a while, the crowd is more spread out, more mixed, more distributed across the available space. There are many more ways for the room to look ordinary once everyone is scattered than there were when all attention was focused in one place. That simple difference between a highly constrained arrangement and a much more widely available range of arrangements is part of the intuition behind entropy. Now bring that way of thinking down to the microscopic world. A physical system, whether it is a gas, a solid, a liquid, or something more exotic, can be in many possible microscopic states. Even if it has a well-defined temperature and pressure and volume, there may still be enormous numbers of ways for its atoms or molecules to arrange their energies and positions while producing the same broad appearance at our scale. Entropy is tied to that multiplicity. It is tied to how many ways the microscopic details can be arranged consistent with the macroscopic condition. This is why entropy often tracks with what we informally call disorder, but the word disorder can be a little misleading if it makes you think the concept is merely visual or subjective. A deck of cards scattered randomly across a table looks disordered to us because we notice the lack of pattern. But in physics, what matters is not whether a human observer finds a scene neat or messy. What matters is how many microscopic possibilities correspond to the state in question. A state with many accessible configurations has higher entropy than one with very few. The universe is not offended by untidy rooms. It is simply more likely to occupy states that can be realized in many ways rather than states that require very special arrangements. That idea becomes incredibly important for heat and temperature because thermal systems are full of particles constantly exchanging energy. The warmer a system is, the more energy is available to distribute among its many possible motions and states. At higher temperatures, there are more ways for a system to arrange that energy. More vibrational modes can be excited, more particles can occupy higher energy states, more microscopic possibilities are open. In broad terms, higher temperature often means higher entropy, though the exact details depend on the system. When you cool something, you're not just lowering its temperature, you're also restricting the range of thermally accessible microscopic arrangements. You're guiding the system toward fewer and fewer allowed ways of sharing its energy. This is where the resistance begins. Nature is not actively trying to annoy scientists, tempting though that interpretation may occasionally be in the laboratory. The resistance is statistical and structural, not emotional. systems tend to evolve towards states that are more probable, and more probable usually means states compatible with more microscopic arrangements. Heat spreads because there are far more ways for energy to be dispersed than concentrated. A hot object cools in a cooler room because energy shared out between object and environment corresponds to a much more typical situation than all that extra thermal energy remaining confined in one place. A gas released into a larger space expands because there are many more ways for its particles to be spread out than clustered in one corner. Again and again, what we see as the natural direction of things is closely related to the fact that some arrangements are overwhelmingly more numerous than others. Cooling a system, especially cooling it to extremes, means fighting that tendency in a controlled way. It means taking a system and carefully reducing the number of thermally available configurations. It means persuading energy to leave, disorder to diminish, and accessible states to narrow. That is not impossible in itself. Refrigerators do it every day. Cryogenic systems do it far more impressively. But the closer you push toward absolute zero, the more severe that narrowing becomes. You're not merely tidying the room, you're asking the system to approach a condition of extraordinary restriction. There is a useful everyday comparison here. It is easy to make a crowded room slightly more orderly. You can ask people to form a line, you can stack chairs, you can gather cups into one place. A little order is not too hard. But making the room perfectly organised in every detail is another matter. Every misplaced item stands out. Every small disturbance matters. Every person walking through the room threatens to undo the arrangement. The closer you get to perfect order, the more fragile the result becomes and the more effort each further improvement requires. In a loose way, something similar happens with entropy at low temperatures. Large reductions are possible. Smaller and smaller further reductions become harder to achieve cleanly. Another way to see this is to think about energy levels in a system. At ordinary temperatures, many of these levels or states may be populated because thermal energy is abundant enough to excite the system in lots of different ways. Lower the temperature, and some of those excitations disappear. Fewer states remain significantly occupied. The system is pushed downward into lower energy configurations. So far, so good. But as more and more of the higher energy possibilities are emptied out, the remaining thermal structure becomes harder to simplify further. You've already removed the obvious excitations. What remains is closer to the minimum pattern allowed. The available entropy shrinks, and with it the room for easy cooling. This is why entropy and cooling are so closely connected. To cool a system, you generally have to remove energy and also deal with entropy. In real processes, those two tasks are linked. The entropy associated with thermal motion must go somewhere. If you reduce it in one place, it typically has to be exported or compensated elsewhere. A refrigerator lowers entropy inside its cold compartment, but only by increasing entropy outside it through the expelled heat and the energy consumed in the process. The overall accounting still respects the laws of thermodynamics. Order bought locally is paid for globally. At ordinary temperatures, this trade is manageable. The outside environment is large and forgiving. The heat dumped into the room from a refrigerator does not cause a family crisis unless the kitchen is already suffering through summer and poor ventilation. But near absolute zero, the bookkeeping gets much stricter. The closer the system gets to the lowest temperature limit, the less entropy remains to be removed, yet removing that last little bit becomes disproportionately demanding. The entropy scale does not behave like a gentle slope all the way to the bottom, it tightens. This tightening is not just some vague inconvenience, it is tied to one of the deepest patterns in thermodynamics, the fact that real processes are never perfectly ideal. They involve irreversibility, friction, gradients, leaks, imperfect couplings, finite times. All of these produce entropy somewhere. Even when your goal is to reduce entropy in the system you care about, the act of doing so can generate entropy in the apparatus or the surroundings. That means you cannot simply march to absolute zero by a straightforward series of practical operations and expect each one to be clean. Every real step costs something. Suppose, for example, you try to cool a material by bringing it into contact with something colder. At first, this works in the usual way. Energy flows out, temperatures approach each other. But if you want to keep going lower, you need a colder stage to hand the system off to, and then a colder one again. Each stage must be prepared. Each connection must be managed. Each step risks generating entropy through non-ideal behaviour. The more stages you require, the more opportunities there are for imperfection. So the path towards deep cold is not merely a question of patience. It is a question of how cleanly thermodynamic operations can be performed, and nature does not offer perfect cleanliness for free. There is also a conceptual point that helps explain why entropy feels like a kind of quiet resistance rather than a dramatic barrier. When people hear that absolute zero cannot be reached, they often imagine a hard wall, something abrupt and visible. But entropy does not stop you that way. It works more subtly. It makes each improvement smaller. It makes the required precision greater. It makes the final state narrower and less accessible. It makes your real-world procedures bleed away ideality. The resistance is not a slap. It is a gradual tightening of conditions until the remaining distance cannot be closed by finite means. That is why the word quiet fits rather well here. Nature doesn't shout no. It simply keeps making the request more unreasonable. Want to go lower? Fine. Remove more energy. Control more couplings. Reduce more stray heating. Manage entropy more carefully. Keep the system closer to equilibrium. Avoid irreversible losses. Improve the apparatus. Slow down the process. Now do it again. And again. And still the endpoint remains ahead. At this stage, it is helpful to distinguish order from stillness, because they are related but not identical. When we talk about lower entropy at low temperatures, we are often talking about a narrowing of accessible states and a reduction of thermal randomness. But that does not mean a system has become dead, empty, or featureless. Quite often the opposite is true. Lower entropy conditions can reveal more delicate forms of organisation. A crystal structure may become more pronounced. Magnetic moments may align in distinctive ways. Quantum systems may enter coherent collective states. Superconductors and superfluids are not boringly still. They are highly structured. The reduction of thermal disorder allows more subtle patterns to become visible. This is one reason low-temperature physics can be so surprising. Common sense says colder means less happening. Physics replies that colder can also mean less noise, and therefore more visible structure. The fading of thermal agitation can uncover behaviours that were previously hidden in the crowd. That does not remove entropy from the story, it sharpens it. A system with lower thermal entropy may become more organised in a very specific way, but that organisation is still governed by the allowed microscopic states, and by the thermodynamic costs of reaching them. Now, as temperature approaches absolute zero, the entropy of a perfect crystal is often said to approach a minimum value. The important point for our purposes is not to memorise formal statements, but to understand the direction of travel. As the temperature falls, the thermal contribution to entropy drops. There are fewer excited states, fewer random thermal arrangements significantly populated. The system is pushed toward its ground behaviour, and because the entropy is becoming so small, each remaining bit matters more. Each stray contribution stands out. Each irreversible step becomes a larger fraction of the total problem. This helps explain something that might otherwise seem paradoxical. If there is less entropy left at very low temperatures, should it not be easier to remove? Surely a small remainder is easier to deal with than a large one. But in practice, the smaller remainder is often more difficult precisely because it is tied to increasingly delicate distinctions between states, and because the procedures used to remove it are never perfect. It is like trying to clear the final grains of dust from a polished surface in a windy room. There is not much left, but that does not make success easy. The standards have become severe, and the environment is not cooperating. Entropy also explains why spontaneous warming is easier to find in nature than spontaneous extreme cooling. Energy spreads out on its own because spread out arrangements are overwhelmingly more numerous. A hot cup cools. A warm room does not spontaneously gather all its thermal energy into one corner and freeze your hat while leaving the rest pleasant. That would require an absurdly special rearrangement of microscopic states. So if you want lower entropy locally, especially very much lower, you have to engineer it. You have to guide the system through carefully chosen processes. The more extreme the reduction, the more your engineering must compensate for the ordinary probabilistic drift of the world. Seen this way, absolute zero is not just the coldest temperature, it is the limit of thermodynamic purification. It is the imagined state where thermal entropy has been driven as far down as the laws permit. And because entropy is so deeply tied to the multiplicity of microscopic possibilities, reaching that limit would mean corralling the system into an extraordinarily constrained condition. That is why the universe resists. Not because it has preferences in any personal sense, but because the entire statistical structure of matter favours the broader spread of possibilities over the absolute narrowing toward one final thermal endpoint. There is another detail worth noticing here. When we say entropy tends to increase, it can sound as though order is always doomed, and every system must slide inevitably toward featureless mush. But real physics is more interesting than that. Local order can absolutely arise. Snowflakes form, crystals grow, living organisms build and maintain astonishing structure. Low-temperature systems produce beautiful phases of matter. What the laws require is that the total accounting, including environment and energy flows, still works out. Local order is not forbidden. It is expensive. It requires pathways, gradients, or surroundings that absorb the thermodynamic cost. That observation helps keep the story grounded. When a cryogenic experiment creates a highly ordered low-temperature state, it is not violating the tendency toward higher entropy overall. It is using carefully designed equipment, energy input, and controlled dissipation to shepherd one part of the world into a very special condition while paying the thermodynamic bill elsewhere. That is why low-entropy states are so scientifically valuable. They are rare, informative, and labour-intensive. They reveal what matter can do when the usual thermal scramble has been suppressed. And yet the bill keeps getting harder to pay the lower you go. That is the heart of nature's quiet resistance. Every stage toward deeper cold demands more selective control over energy and entropy. Every small gain requires cleaner operations and better isolation. The system must be protected not only from outside warmth, but from the entropy-producing imperfections of the cooling process itself. No matter how refined the method, each finite step remains a real process with real limitations. That is why entropy belongs at the centre of this story. Without it, absolute zero might look like a purely technical challenge, a matter of building a better machine. With entropy in view, we see that the challenge is deeper. It is about the statistical architecture of matter. It is about the tendency of systems to occupy what is broadly available, rather than what is microscopically singular. It is about the fact that thermal energy does not merely need to be reduced. The accessible spread of states must be narrowed toward an extreme limit, and that narrowing becomes harder and harder to accomplish by real means. So when we speak of order, disorder, and the difficulty of reaching perfect cold, we are really describing a contest between human control and the natural abundance of microscopic possibilities. We can reduce the spread, we can lower the temperature, we can coax systems into remarkable low-entropy states. But the final thermodynamic quiet remains out of reach, because the closer we get, the more exacting the task becomes, until the laws themselves tell us that the endpoint cannot be completed through any finite series of physical operations. And once entropy has led us that far, there is really only one place for the story to go next. Because the idea that absolute zero cannot be reached is not just an impression or a practical complaint from tired experimentalists. It is codified in one of the formal laws of thermodynamics. The resistance we have been describing has a name, a structure, and a place in physics that makes it impossible to dismiss as mere engineering bad luck. It is time now to look directly at that law and see how it turns the chase for perfect cold into an unreachable limit written into the foundations of thermodynamics itself. By the time physicists had spent enough years pushing matter into colder and colder territory, a pattern had become impossible to ignore. The lower the temperature, the stranger the effort required to go lower still. Cooling did not fail in a dramatic way. There was no final clang, no red warning light from the universe, no icy gate marked "Do Not Enter." Instead, there was a steady tightening. Each step demanded more precision. Each method gave less in return. Each gain came with a bigger bill in complexity, patience, and control. At some point, this stopped looking like a practical inconvenience and started looking like a law. That is where the third law of thermodynamics enters the story. Not as a piece of academic decoration, and not as one of those laws whose name sounds important mainly because it contains the word law, but as a real statement about how nature behaves near the bottom of the temperature scale. The third law is one of the reasons absolute zero is not merely difficult to reach. It is unreachable in principle by any finite physical process. You can approach it. You can move astonishingly close. You can build machines and experiments of almost absurd ingenuity. But the last step does not belong to the kind of world we actually inhabit. Now, like many famous scientific laws, the third law can sound more intimidating than it really is if it is introduced too abruptly, so it helps to ease into it from the side rather than charging at it head first. The central idea is connected to entropy, which we have already been getting acquainted with. As the temperature of a system drops, the thermal randomness associated with all those excited microscopic arrangements becomes more limited. Fewer energy states are significantly occupied. The system settles toward its lowest available behavior. In a very idealized case, such as a perfect crystal, the entropy approaches a minimum value as the temperature approaches absolute zero. That is one common way of expressing the third law. Another, equally important way of expressing it is the unattainability principle. No finite sequence of physical operations can bring a system all the way to absolute zero. That version is especially useful for our story because it connects the law directly to the human pursuit of cold. It says in effect that there is no clever shortcut hiding just out of view. No matter how advanced the method, no matter how refined the apparatus, no matter how many stages of cooling you stack on top of one another, absolute zero cannot be completed as an achievement. This is not because scientists have run out of ambition. It is not because laboratory budgets eventually begin to complain in a language administrators understand. It is because the structure of thermodynamics itself refuses the final completion. Real cooling procedures always involve finite steps, finite times, finite couplings, finite control. The third law tells us that these are never enough. There is something almost irritatingly polite about how nature makes this refusal. It does not say no with a bang. It says nearly, again and again, forever. You can make a gas colder. You can make a solid colder. You can cool trapped atoms to temperatures that would sound like typographical errors to anyone outside the field. But the law sits beneath all of that progress and quietly insists that the endpoint remains ahead. Historically, this realization did not arrive all at once. Thermodynamics itself was built gradually through the study of heat engines, work, energy transfer, and the behavior of matter under changing conditions. The first and second laws of thermodynamics already gave scientists a powerful framework for understanding why energy is conserved and why natural processes have preferred directions. Heat flows from warmer to cooler. Entropy tends to increase overall. Engines have limits. Refrigerators require work. Those laws explained a great deal, but as experiments pushed deeper into low-temperature regimes, it became clear that there was more to say about the behavior of matter near the absolute floor. One of the key figures in this story was Walter Nernst, whose work in the early 20th century helped crystallize what became known as the heat theorem. Without getting lost in the historical details, the important point is that scientists recognized a pattern in how entropy changes as temperature drops towards zero. The thermal disorder does not just diminish in a casual way. It approaches a limiting structure. The lower end of the temperature scale is not open and indefinite, it is constrained. The third law emerged as a way of expressing that deep constraint. Now, if you hear that entropy approaches a minimum at absolute zero, it may be tempting to think of the matter in question as becoming completely simple, perfectly silent, perhaps even a little dull. But low-temperature physics has a habit of punishing that kind of expectation. The approach to absolute zero is not dull at all. It is one of the richest regions in all of science because as thermal noise fades, the underlying organization of matter becomes easier to see. The third law does not describe a boring endpoint so much as a narrowing into a highly constrained domain where ordinary thermal confusion no longer hides the deeper structure. Still, let us stay close to the practical meaning. Suppose you have some system you want to cool. At ordinary temperatures, there are many available thermal excitations. The particles can occupy many energy levels, vibrations are lively, collisions are frequent, and there is plenty of entropy associated with all that microscopic possibility. When you cool the system, you remove energy and reduce the range of excited behavior. Fine, you can continue doing that for a while, but as the system gets colder, the remaining excitations become fewer and more delicate. The entropy left to remove shrinks. The available lower energy states dominate more strongly. The process becomes increasingly exacting. The third law tells us that this exacting character is not just a technical annoyance, it is intrinsic. To reach absolute zero would require a complete elimination of thermal entropy in the ideal sense, but any real procedure you use to try to achieve that involves imperfect operations. There is always some irreversibility. There is always some finite limitation. There is always some residual coupling, some tiny source of warming, some imperfect exchange. Even if each individual imperfection is minuscule, the law says that finite procedures cannot close the remaining gap. A helpful comparison might be trying to flatten every wrinkle from a sheet laid across a bed in a room with a breeze coming through the window. At first the big wrinkles are easy. You pull the corners, smooth the surface, and the sheet looks much better almost immediately. Then the smaller creases remain. You smooth those too. Then you notice tiny ripples, barely visible but still present. To remove them completely you need finer control, steadier hands, less disturbance from the air. The closer you get to perfection, the more any tiny interference matters. But unlike the sheet, where in principle you might eventually win if the room becomes still enough, the third law says the thermodynamic room never grants you that final complete stillness through finite means. This is why absolute zero behaves more like a horizon than a destination. A horizon is not imaginary. It is real in the sense that it structures your view. You can orient yourself by it. You can move toward it. It changes what is visible, but you do not arrive at it by ordinary travel. In much the same way, absolute zero is a real limit that organizes the temperature scale and governs the behavior of matter near the bottom, but it does not become an attained point in the ordinary physical sense. There is also an important subtlety in how the third law is phrased for idealized systems versus real materials. In the simplest textbook version, a perfect crystal has entropy approaching a specific minimum at absolute zero. That ideal image is useful, but real materials can be messier. Some have residual disorder built into their structure. Some can get trapped in configurations that prevent them from reaching the most perfectly ordered state. Glasses, for example, are notorious for retaining a kind of structural disorder even at low temperatures. So the third law is not merely a claim that every actual piece of matter becomes a pristine ideal crystal if only you cool it enough. Rather, it tells us about the limiting thermodynamic structure and the unattainability of the endpoint. The details of real substances may vary, but the lower limit remains stubbornly protected. That matters because it prevents a common misunderstanding. Someone might hear that entropy approaches a minimum at zero temperature, and imagine that if only we found the right material, perhaps one especially well-behaved substance would slip cleanly all the way down. The third law says no. The law is not waiting for the right chemistry to be flattered into cooperation. Different systems may approach the limit in different ways, but the unattainability remains. Another way to appreciate the force of the third law is to notice how it changes the meaning of cooling time. At everyday scales, we assume that given enough time, many physical processes just finish. A hot pie cools. A warm car eventually matches the temperature of a garage. A room settles after the heater is turned off. But near absolute zero, the third law tells us that the time and number of operations needed to continue lowering the temperature become effectively unbounded if your goal is the exact endpoint. The closer you get, the slower progress becomes. In a practical sense, it is as though the finish line keeps retreating just enough to deny completion. This retreat is not arbitrary. It is linked to the fact that the response of systems changes at low temperatures. Heat capacities can become very small. Thermal conductivities may behave differently. Relaxation times may grow. Couplings between the part you want to cool and the cooling apparatus can weaken in troublesome ways. Degrees of freedom that seemed well behaved at higher temperatures no longer exchange energy efficiently enough. The whole process becomes less like draining a bathtub and more like trying to remove the final trace of moisture from a surface, while the air itself keeps putting some back. Then there is the issue of reversibility, one of those words that sounds harmless until you realize thermodynamics is using it in a very strict way. An ideal reversible process is an almost impossibly gentle one, carried out so slowly and cleanly that no unnecessary entropy is generated. Such processes are useful as conceptual limits. They tell us what perfect efficiency would look like if nature were willing to indulge us. Real processes, of course, are not like that. Real cooling involves finite rates, finite gradients, and all manner of small imperfections. To hit absolute zero would require a level of ideal reversibility that finite operations cannot provide. The third law is, among other things, a statement about the failure of real procedures to impersonate thermodynamic perfection at the endpoint. There is something almost comforting in how unromantic that is. Physics does not say absolute zero is unreachable because it is mystical or sacred or beyond mortal grasp in some melodramatic sense. It says it is unreachable because the thermodynamic accounting never comes out exactly right under finite procedures. That is somehow both less dramatic and more impressive. The universe does not need poetry to defend its limits. Bookkeeping will do. Of course, scientists are rarely content with a law unless they can also test how closely reality obeys it. And this is where low-temperature physics becomes such a triumph of experimental persistence. Researchers have pushed temperatures down to extraordinary fractions of a Kelvin above absolute zero. In some atomic systems, they have reached regimes so cold that thermal motion is all but drowned out by quantum behavior. In condensed matter systems, they have explored millikelvin and microkelvin territories where entirely new phases of matter emerge. Each of these achievements is a victory not against the third law, but under it. The law does not prevent dramatic progress. It prevents exact completion. This distinction matters. When people hear unreachable, they sometimes imagine useless. But unreachable limits in physics are often among the most productive ideas we have. The speed of light plays a similar conceptual role in a different domain. Mass can be accelerated to speeds astonishingly close to it, and that very closeness teaches us tremendous amounts about energy, motion, and relativity, even though the final limit remains closed. Absolute zero functions in a comparable way. It is a boundary that shapes the whole field. Approaching it reveals new physics. Failing to reach it is not a disappointment. It is part of the lesson. What the third law really gives us, then, is a deep answer to an old human instinct. We like to assume that if something can be approached, it can eventually be reached. Enough effort, enough refinement, enough technology, enough patience. That instinct works well often enough in daily life that it becomes a habit of thought. But thermodynamics teaches a more disciplined perspective. Some limits are asymptotic. Some goals recede under finite operations. Some edges of physical possibility organize the world precisely by refusing to become ordinary destinations. This also explains why the Kelvin scale feels so unusual. 0 Kelvin is not merely the place where we started counting. It is the lower limit whose unattainability is guaranteed by the third law. Every positive temperature on that scale is a statement of distance above a floor that no finite process can quite touch. A system at 1 Kelvin is unimaginably colder than anything in ordinary experience, but from the viewpoint of the law, it still sits above the horizon. So does a millikelvin. So does a microkelvin. So does every measured triumph of low-temperature engineering. The numbers shrink. The law remains patient. There is a nice irony here as well. The closer experiments come to absolute zero, the less the world resembles the everyday idea of frozen stillness. Instead, quantum phenomena become clearer. Matter can become more coherent, more collective, more revealing. The unattainable limit does not lead into emptiness but into strangeness. The third law bars the door to perfect thermal silence, yet in doing so it opens a vast territory of near silence where the deeper rules of matter finally become audible. That is one of the reasons the third law deserves more affection than it usually gets. It is often introduced late in thermodynamics courses, as though by that point everyone is already too tired to object and will simply accept another formal statement on trust. But it is actually a beautiful law because it ties together so many threads: entropy, low-temperature behavior, the meaning of the Kelvin scale, the practical challenge of refrigeration, the impossibility of finite completion, the emergence of new physics near the edge. It is not an extra rule tacked on for completeness. It is the quiet verdict on the whole chase. And perhaps the most satisfying part is that the law does not merely tell us what cannot happen. It tells us how to think about the approach itself. If absolute zero is unreachable, then the interesting question is not why have we failed so far, but what does matter do as we get ever closer? The answer is that thermal agitation fades, entropy narrows, ordinary assumptions begin to break, and quantum rules stop acting like footnotes and take the main role instead. The unattainable limit becomes the stage on which the most delicate forms of physical behavior appear. So when we say the third law of thermodynamics turns absolute zero into an unreachable limit, we are not simply repeating a famous phrase. We're naming the principle that explains why every real cooling process stalls into diminishing returns, why no finite chain of operations can complete the final descent, and why the lower end of the temperature scale is not just colder, but fundamentally different. The law gives structure to the impossibility. It tells us that the universe does indeed have a coldest boundary, and that boundary is real enough to govern experiments while still withholding itself from full occupation, which leaves us standing in a very interesting place. We now know that the endpoint cannot be reached, and we know that thermodynamics is the reason. But there is still another layer underneath that story, because even if you ignored practical imperfections and imagined the most perfectly controlled descent, matter would still refuse to become classically motionless. Something remains, something irreducible. The next step is to look directly at that remaining restlessness and see why, in the quantum world, complete stillness never truly arrives. And this is the point where the story becomes even stranger, because once we've followed thermodynamics all the way down to the edge of its warning, another voice joins in. Thermodynamics tells us that absolute zero cannot be reached by any finite process. Quantum mechanics then adds something even more unsettling. Even if you imagine matter brought as low as the laws allow, it still does not become the perfectly still, perfectly silent thing our ordinary intuition keeps trying to picture. The final quiet, in the strict everyday sense, never truly arrives. That can feel almost unfair the first time you hear it. After all, we have spent so much of this journey treating temperature as a measure of thermal motion, Hotter means more microscopic agitation. Colder means less. So it is only natural to imagine that if we keep reducing temperature, the motion should keep fading until it vanishes. The particles should finally settle down. The dance should end. The stage should empty. The universe should, for one brief, impossible moment, stop fidgeting. But the quantum world does not work that way. This is one of the great recurring lessons of modern physics. Whenever we push an everyday idea to its extreme, we find that nature has signed the agreement only up to a point. Matter can become colder. Motion can be reduced. Thermal agitation can be stripped away to astonishingly low levels. Yet perfect stillness, the classical dream of every particle sitting there with no remaining uncertainty, no residual motion, no hidden activity, turns out not to be a physically allowed condition for ordinary bound matter. To see why, it helps to start with something simple. Imagine a particle trapped in some region of space, not drifting freely across the universe but confined, held in place by forces, bound into an atom perhaps, or bound within a solid, or trapped in some controlled experimental arrangement. In the everyday picture, we might imagine that if we remove enough energy, that particle should eventually just sit there exactly where it is, with no motion at all. Like a marble placed gently at the bottom of a bowl, finally coming to rest. That image is comfortable, but quantum mechanics does not permit it in the neat way we want. A quantum particle is not a tiny hard bead with a perfectly definite position and a perfectly definite state of rest waiting patiently to be assigned. Its behaviour is described in a more subtle way. There are limits to how sharply position and motion can both be specified at the same time. The more tightly a particle is confined, the less the idea of perfectly exact zero motion makes sense. Nature refuses to let you pin everything down with unlimited precision and then declare the problem finished. This is the part often summarized by the uncertainty principle, which has been repeated so often in popular science that it sometimes sounds like a philosophical slogan rather than a precise physical fact. But here it matters in a very concrete way. If a particle were perfectly still in the classical sense, with absolutely no residual motion, then its momentum would be exactly fixed at zero. If at the same time it were tightly localized in a definite place, as bound particles in real materials generally are, that would violate the basic quantum structure of how such quantities are related. The world is simply not built to allow both of those demands at once. So the lowest energy state of a bound system is not the same thing as perfect classical rest. It is the ground state, the minimum energy state allowed by the system, and that state still carries a kind of irreducible motion or fluctuation. The particle is not free to do whatever it likes, but neither is it frozen into a mathematically exact still point. There remains a baseline restlessness built into the quantum description itself. This can sound abstract until you apply it to something familiar. Consider atoms in a solid. In a simple picture, each atom sits near a preferred position in the material structure, held there by interactions with neighbouring atoms. At everyday temperatures, those atoms vibrate significantly. Warm the solid and the vibrations grow. Cool it and they diminish. Fine. That part matches intuition well enough. But when the temperature becomes extremely low, those vibrations do not just shrink smoothly to nothing. Even in the lowest possible state, the atoms still possess a residual vibrational character. Not because the material is badly made, not because the experiment failed, not because some hidden heater is under the table, simply because the quantum ground state of the system is not complete stillness. This is sometimes called zero-point motion, and it is one of the most quietly important ideas in the entire story of absolute zero. It means that even when all thermal motion that can be removed has been removed, some motion remains, not as heat in the ordinary sense, but as the minimum activity required by quantum mechanics. Matter at the lowest accessible temperature is not a dead sculpture. It is matter in its ground state, and the ground state still has structure, energy, and fluctuation. There is something almost mischievous about that. We go searching for the point where motion ends, and quantum theory says motion in the classical sense was never the full story to begin with. The microscopic world was always going to keep a little mystery in reserve. A very useful way to picture this, without wandering into mathematical language, is to imagine again the marble in a bowl. In an ordinary classical world, the marble can roll down to the bottom and stay there exactly at rest. Its position is clear. Its motion is zero. End of drama. But in the quantum version, the marble is not really a marble and the bowl is not really a bowl. The particle behaves like something with wave-like properties, as well as particle-like ones. If you try to confine it at the exact bottom with perfect stillness, the description no longer works. The ground state becomes more like a minimum cloud of possibility centered around the lowest point, with the least energy allowed, but not a perfectly still pinpoint. That cloud is not just a bookkeeping trick, it has real consequences. It affects the behavior of atoms and solids. It contributes to the properties of helium at low temperatures. It influences chemical bonding and the stability of matter. In other words, the fact that stillness never fully arrives is not merely a philosophical footnote near absolute zero. It is woven into the ordinary existence of the material world. Helium is a particularly beautiful example. Most substances, if cooled enough, become solid under the right pressure. Their atoms settle into ordered arrangements because thermal agitation is no longer vigorous enough to resist it. Helium is different in a striking way. Because helium atoms are so light, and their quantum motion is so prominent, ordinary helium remains liquid all the way down to extremely low temperatures unless additional pressure is applied. In other words, even the coldest accessible conditions do not automatically force helium into the behavior our everyday intuition might expect. Its atoms retain enough quantum restlessness that they resist freezing under normal pressure. That is not thermal warmth sneaking back in. That is the quantum character of matter refusing to impersonate a classical solid. This helps us separate two ideas that are easy to blur together. Thermal motion is the random energy associated with temperature. Quantum motion, in this context, is the residual activity built into the ground state of a bound system. The first can be reduced by cooling. The second is not something cooling can simply erase. So when we say temperature measures microscopic motion, that is true in the thermal sense. But when temperature approaches its lowest limit, the remaining behavior is no longer well described as ordinary heat. It is the irreducible baseline beneath heat. That difference matters, because it keeps us from making a common mistake. People sometimes hear that particles still move near absolute zero and imagine that the system must therefore still be warm in some hidden way, as though the refrigerator simply missed a spot. But that is not what is happening. Residual quantum motion is not the same thing as leftover thermal agitation. The system can be in its lowest thermal state and still display ground state fluctuations. The failure of perfect stillness is not a failure of cooling technique. It is a feature of reality. This is one reason the low temperature world becomes more obviously quantum as thermal noise fades away. At room temperature, ordinary materials are full of thermal commotion. There is so much activity that subtle ground state effects are often masked. As the temperature drops, many of those thermal excitations disappear, and what remains more clearly reflects the underlying quantum structure of the system. It is almost like lowering the volume on a crowded room until you can finally hear a faint but persistent sound that had been there all along. That faint sound is not always literal motion in the simple sense. Sometimes it is best understood as residual energy, or fluctuations in fields, or the non-classical character of a ground state. But the broader point remains. Matter does not become classical and perfectly settled at the bottom. It becomes recognizably quantum. This is also why some of the most exotic phases of matter appear at ultra-low temperatures. Superconductors, for example, do not simply become colder metals. They enter a collective quantum state in which electrical resistance vanishes under the right conditions. Superfluids do not merely become colder liquids. They begin flowing with astonishing properties that make ordinary fluid behavior look clumsy by comparison. Ultra-cold atomic gases can condense into states where huge numbers of atoms occupy the same quantum condition, and behave with extraordinary coherence. These are not signs that the system has become featureless. They are signs that thermal disorder has receded enough for the quantum rules to take centre stage. There is a certain irony in that. The closer we get to the coldest limit, the less the world resembles the ordinary idea of frozen silence. Instead, it becomes richer in specifically quantum behaviour. Less thermal motion does not mean less happening in every sense. It means less random noise. And when the noise fades, the deeper organisation of matter becomes easier to see. Now, none of this by itself is the full reason absolute zero cannot be reached. The third law already gave us the thermodynamic verdict. No finite process can complete the final descent. But quantum mechanics explains why the endpoint, even as an ideal, should not be imagined as perfect classical stillness. The unattainable limit is not merely hard to reach, it is also subtler than intuition expected. The bottom of the scale is not a static graveyard of motion, it is a ground state world of minimum allowed activity. You can think of it this way. Classical intuition says cooling should gradually remove movement until nothing remains. Thermodynamics says the exact endpoint cannot be attained by finite means. Quantum mechanics then adds that the state you were picturing at the endpoint was never quite the right picture anyway. Even in the lowest possible state, the microscopic world retains an irreducible thickness, a residual blur, a minimum liveliness that cannot be ironed flat. There is something deeply important about that blur. Without it, many systems would collapse into pathological simplicity. Atoms themselves depend on quantum structure for their size and stability. Electrons do not simply fall into nuclei because the quantum rules governing bound states prevent such a crude classical collapse. Matter is not stable in spite of quantum uncertainty and ground state structure. It is stable because of them. So the same principles that deny us perfect stillness are also part of what make the ordinary world possible. That realization can be strangely comforting. The universe is not frustrating us out of spite. It is being consistent. The quantum rules that prevent total stillness near absolute zero are the same sort of rules that give matter its resilience, its architecture, and its refusal to behave like a pile of tiny solar systems with better manners. Even so, the imagination still wants to ask one more question. If there is always some residual motion or fluctuation, does that mean absolute zero itself is meaningless? Not at all. Absolute zero remains the lower limit of thermodynamic temperature. What changes is our understanding of what that lower limit represents. It does not correspond to all motion vanishing in the broadest imaginable sense. It corresponds to the absence of removable thermal excitation, the approach to the ground state, the minimum thermal condition allowed. Quantum motion can remain without contradicting that. In fact, it is exactly what the quantum world requires. That is a subtle distinction, but a very important one. Temperature and motion are related, yet not every kind of microscopic activity maps neatly onto the everyday idea of heat. At ordinary conditions, we can get away with speaking loosely. Hot means lively. Cold means calm. Near absolute zero, the loose language starts to wobble. What is disappearing is thermal randomness. What remains is the structure of the ground state. The system is quieter, but not mute. And once you begin to think in those terms, the question of why absolute zero can never be reached starts to feel less like a single obstacle, and more like the convergence of two different truths. Thermodynamics blocks the final approach through the logic of entropy and unattainability. Quantum mechanics denies the fantasy of perfect classical stillness even in the lowest state. Together they form a remarkably strong answer. We cannot get to absolute zero by finite means, and even the state we aim toward is not the simple empty silence we first imagined. This convergence also explains why low-temperature research is so productive. Scientists are not merely trying to make things cold for the sake of claiming a lower number. They are probing the territory where thermal effects fade and quantum behaviour becomes cleanly visible. The inability to reach the exact endpoint does not make the effort less valuable. It makes the near endpoint more interesting. Every fraction closer strips away more thermal distraction. Every reduction reveals more of the system's ground state character. The horizon remains unreachable, but the landscape near it is extraordinarily rich. That is why laboratories continue to chase lower and lower temperatures with such determination. Not because they expect one final heroic experiment to overthrow the laws of nature, but because what happens near the limit is scientifically priceless. Near the bottom of the scale, matter behaves in ways that can test fundamental theory, enable new technology, and reveal phases of matter that simply do not exist in warmer conditions. The remaining quantum motion is not a nuisance spoiling the picture, it is part of the picture. There is also a quiet lesson here about the limits of common sense. We are creatures of the middle range. The temperatures we evolved to care about are weather temperatures, body temperatures, cooking temperatures, seasonal temperatures. In that world, cold really does seem like the slowing down of everything towards stillness. Physics does not mock that intuition. It simply tells us where it stops being reliable. At the deepest levels, matter is not made for perfect rest in the classical sense. It is made of quantum states, constrained possibilities, and ground state fluctuations that do not ask for our approval. So when stillness never fully arrives, that is not a failure of the theory. It is one of its clearest triumphs. The universe is telling us, through the behavior of ultra-cold matter, what its basic grammar actually is. Not rigid points and precise trajectories settling into final rest, but quantized systems with minimum energies, residual fluctuations, and an irreducible refusal to become perfectly definite in all the ways our intuition would prefer. And perhaps that is the most elegant part of the whole story. We began with the idea of cold as the simple opposite of heat. We refined that into temperature as microscopic motion. We followed cooling into entropy, thermodynamics, and the unattainable limit. Now, at the edge of the possible, we discover that the remaining activity is not accidental. It is fundamental. The final quiet is replaced by a deeper kind of order, one that still shivers, still fluctuates, still resists our dream of perfect mechanical peace. That leaves us in a very revealing place. We now know why the endpoint remains beyond reach in principle, and we know why matter would not become classically motionless even at the lowest thermal boundary. The natural next step is to look at how close human beings have actually managed to get, because once you understand how forbidding the final distance is, the achievements of modern laboratories start to look almost unbelievable. We have not reached the bottom, but we have approached it closely enough to build some of the coldest places the universe has ever known. And the methods used to create them are every bit as strange and ingenious as the physics they uncover. By now, the idea that absolute zero can never be reached may sound almost severe, as though physics has spent this entire journey patiently explaining the rules, only to end by taking the ladder away. But one of the loveliest twists in the story is that even though the final limit remains out of reach, human beings have still managed to get astonishingly close. Close enough that the temperatures involved stop sounding like ordinary cold and start sounding more like an argument with reality. Close enough that the warmest parts of empty space begin to look positively cozy by comparison. Close enough that matter starts behaving in ways no kitchen freezer, winter storm, or block of ice could ever prepare you for. And perhaps that is the right way to think about the coldest places we have ever made. They are not natural extensions of familiar cold. They are not just more winter. They are not a stronger version of the unpleasant moment when you touch a metal railing without gloves and immediately regret your confidence. They are environments so carefully engineered, so aggressively protected from stray heat, that the normal thermal life of the universe has been pushed back almost entirely. These places are not cold by accident. They are cold by strategy. If you were to visit one of the laboratories where such temperatures are produced, the first surprise might be that it does not necessarily look like the inside of an ice cave or some glittering chamber lined with frost. In many cases, it looks more like a forest of cables, metal vessels, vacuum chambers, optical tables, and equipment assembled with the sort of seriousness that suggests everyone involved has been betrayed by a loose screw before and would rather not relive the experience. The cold is not theatrical. It is hidden. The sample itself may be tiny. The coldest region may occupy a small volume deep inside layers of shielding and apparatus. To create one of the coldest places ever made, scientists do not simply build a giant box and turn the temperature down. They build a whole sequence of protections and procedures designed to remove heat from one small system while preventing the rest of the world from putting it back. That is part of what makes these achievements so remarkable. When we say a laboratory has reached some unimaginably low temperature, we do not mean the whole building has become a frozen monument to poor planning. We usually mean that a carefully isolated sample, or cloud of atoms, or electronic device has been brought to that temperature under very specific conditions. The room itself may be comfortable. The researchers may be wearing ordinary clothes. Somewhere in the middle of a very expensive arrangement of hardware, however, a tiny region is sitting in a state colder than vast stretches of outer space. That comparison is worth lingering on, because space has a reputation for being the natural champion of cold. It certainly sounds convincing. Dark vacuum, distant stars, general lack of central heating. But the universe is not uniformly at the lowest possible temperature. There is background radiation everywhere, the faint relic glow of the cosmos itself, and even the emptiest interstellar regions are not at absolute zero. In fact, many of the coldest human-made systems are far colder than the general background of space. That is a delightful reversal. We imagine laboratories as small, local, artificial things, and outer space as the grand cold beyond everything. Yet with enough ingenuity, a human-built apparatus on one small planet can produce conditions colder than nature usually provides across billions of light-years. One route to that achievement runs through dilution refrigeration, which sounds far gentler than the engineering effort it actually represents. These refrigerators are among the workhorses of ultra-low temperature physics, especially in condensed matter research and in the study of quantum devices. They rely on the peculiar behavior of different isotopes of helium at very low temperatures. Without getting lost in excessive detail, the basic idea is that under the right conditions, a mixture involving helium can be arranged so that one part of the system cools as atoms move from one phase into another. The process can continuously remove heat and drive temperatures down into the millikelvin range, tiny fractions of a degree above absolute zero. That may not sound dramatic when phrased so calmly, but it is a profound technical achievement. A dilution refrigerator is not a more enthusiastic household fridge. It is a layered cryogenic machine in which every material, every thermal contact, every support structure, every wire and every stage has to be designed with extraordinary care. The colder regions are hidden inside successively warmer shields, each stage intercepting heat before it reaches the next. Looking at one from the outside, you might not guess that deep in its centre lies a place so cold that ordinary intuition has simply stopped being useful. These refrigerators have become especially important in modern quantum technology, where researchers need to cool superconducting circuits and other sensitive devices to temperatures low enough that thermal noise does not overwhelm the subtle quantum effects they are trying to study. A quantum bit is not likely to appreciate being jostled by the thermal equivalent of a crowded room. To keep such systems behaving coherently, scientists must push them into conditions where heat has largely been evicted from the conversation. The coldest places humans make are often created not merely for the pleasure of claiming a low number, but because certain delicate forms of physics will only reveal themselves when the thermal world has been quieted enough. Another route to extraordinary cold is even stranger, because it involves using light to slow atoms. This still feels slightly impolite to common sense. Light is supposed to illuminate and in many ordinary settings to warm, yet laser cooling turns that expectation neatly around. By tuning laser light with exquisite care, scientists can arrange for atoms moving in certain directions to absorb photons in a way that slows them down. Each interaction removes a little momentum from the atoms, Repeat this with enough precision, surround the atoms with appropriately arranged beams, combine the method with magnetic trapping, and you can cool a cloud of atoms to astonishingly low temperatures. There is something almost surreal about that image. Not because the apparatus is fictional, but because the target of the cooling is so ethereal. You are not chilling a metal block or a flask of liquid. You're creating a sparse cloud of atoms held in place by fields and light, then persuading those atoms to move more and more slowly until their thermal agitation becomes almost vanishingly small. This is not winter cold. This is choreography. Laser cooling alone is often not the end of the process. It can get atoms impressively cold, but to go lower still, researchers may use evaporative cooling in traps. The idea returns, as it so often does, to the old principle that if the most energetic particles are allowed to leave, the ones that remain have lower average energy. In an atomic trap, the highest energy atoms are selectively removed, and the rest of the cloud rethermalizes at a lower temperature. It is a very refined version of the same logic that cools sweat on skin, except now the participants are atoms drifting in a controlled vacuum environment, while physicists watch with the sort of concentration normally reserved for diffusing an argument at a family dinner. These methods led to one of the most celebrated milestones in low-temperature physics, the creation of Bose-Einstein condensates. In such a state, a dilute gas of certain atoms cooled to extremely low temperatures can undergo a remarkable transformation. Instead of behaving like a collection of distinct independent particles in the ordinary sense, the atoms begin occupying the same quantum state and act with a kind of collective coherence. It is one of those discoveries that sounds like it was named before anyone had quite enough sleep, but the physics is beautiful. A gas that should by all ordinary expectations remain simply a gas becomes something more unified, more wave-like, more collective. This is the sort of phenomenon that only becomes visible in the near silence of ultra-cold conditions. When the first Bose-Einstein condensates were produced, it was not just a new record in the pursuit of cold, it was the opening of a new scientific landscape. Suddenly, researchers could study quantum phenomena on scales large enough to manipulate and observe, in ways that had previously seemed impossible. The cloud of atoms behaved less like a conventional thermal sample, and more like a coherent quantum object. That does not happen because we reached absolute zero. It happens because we got close enough to strip away enough thermal noise for the underlying quantum structure to show itself clearly. Over time, scientists have pushed these atomic systems to temperatures unimaginably near the absolute limit. In some experiments, clouds of atoms have been cooled to billionths of a degree above 0 Kelvin. That number is so small that it resists ordinary comparison. There is no weather analogy for it, no culinary analogy, no household object experiences that. These are temperatures achieved not in nature's casual settings, but in carefully tuned traps, with lasers, magnetic fields, vacuums, and measurement methods refined over decades. To say that humans have made places this cold is to say that we have learned how to suppress the thermal life of matter to an extraordinary extent without ever fully extinguishing it. Of course, the phrase place becomes a little flexible here. Some of the coldest places we have ever made are not places you could stand in, or rooms you could enter, or chambers large enough to contain more than a whisper of matter. They are experimental regions, tiny domains where specific particles or samples are prepared under extreme conditions. Still, the word place feels fair in a scientific sense. A place is where a set of physical conditions exists, and in that sense, the coldest places ever made are often smaller than imagination first expects, and stranger than language is comfortable admitting. There have even been efforts to exploit the unusual conditions of space itself for ultra-cold experiments. Microgravity can help researchers study cold atomic systems over longer times and with fewer disturbances of certain kinds. In orbit, ultra-cold atom experiments can be observed as they evolve in ways that would be harder on Earth. This does not mean space hands us absolute zero on a silver tray. Far from it. The challenge of cooling remains. But it does mean that once we have learned to make matter extremely cold, we can carry that skill into environments where the resulting physics becomes even more revealing. What is so striking about all of these achievements is that they are not simply races for the lowest number. Each new record in cooling tends to open a new kind of science. Near the bottom of the scale, materials and particles stop behaving like quieter versions of their ordinary selves and start doing things that reveal their deeper structure. Superconductors become possible. Quantum coherence becomes more robust. Exotic phases of matter emerge. Precision measurements improve. Fundamental constants can be probed. Technologies that depend on delicate quantum behavior become practical or at least imaginable. The coldest places we have ever made are not trophies in a cabinet. They are working laboratories where the rules of nature become easier to read because the thermal handwriting around them has faded. Still, the pursuit remains difficult in a way that is almost comical when described plainly. To make one tiny sample absurdly cold, researchers often need large and complicated systems that themselves sit in ordinary human environments full of warmth, vibration, electrical noise, and entirely too much enthusiasm from the rest of the universe. Heat can arrive through support structures, through radiation, through residual gas molecules, through measurement electronics, through imperfect shielding, through your own optimism if it causes you to underestimate any of the above. The coldest places we have ever made are therefore also some of the most carefully defended. They exist not just because we can remove heat, but because we can hold the line against its return. There is a subtle emotional shift that happens when you start to appreciate this. At first, deep cold sounds like emptiness, as though the goal was simply to make less happen. But the real achievement of these laboratories is not emptiness, it is control. They create conditions in which tiny differences matter, in which quantum behavior can survive, in which matter can reveal arrangements and effects that ordinary temperatures would immediately blur away. The cold is not an absence of science, it is a way of clearing the stage for more science. One of the reasons this is so compelling is that it overturns a quiet assumption many of us carry from daily life. In ordinary experience, colder things often seem less active and less interesting. Soup becomes less fragrant. Batteries become more annoying. Fingers become less cooperative. But at the frontier of low-temperature physics, colder often means more surprising. Not because the particles are suddenly doing more in the thermal sense, but because the reduction of thermal disorder allows hidden forms of order and coherence to appear. The coldest places we have ever made are among the most revealing places we have ever made. There is also something deeply human in the methods themselves. We did not find these places. We assembled them from understanding. We learned what temperature really measures, how atoms move, how heat can be transferred, how entropy resists, how thermodynamics narrows the path, how quantum mechanics shapes the bottom of the scale, and then we built machines that embody all of that knowledge. A dilution refrigerator is a lesson in thermodynamics made metal. A laser cooling setup is a lesson in quantum optics made visible. An ultra-cold atom trap is not just equipment, it is understanding turned into hardware. And perhaps that is why the coldest places we have ever made feel so satisfying as part of this story. They prove that the fact absolute zero is unreachable does not make the pursuit futile. Quite the opposite. The approach itself has transformed modern physics. We have not reached perfect cold, but we have reached conditions so extreme that the universe begins to answer questions it will not answer anywhere warmer. We have made matter colder than much of space. We have produced quantum states once treated as theoretical curiosities. We have cooled systems so deeply that the old everyday meaning of temperature all but dissolves, leaving something more fundamental in view. Even the records themselves, impressive as they are not really the most interesting part. The number matters, yes, but more important is what the number lets you see. A few billionths of a degree above 0 Kelvin is not just a bragging right. It is a doorway into a regime where randomness has been stripped down enough for coherence to dominate, where collective quantum effects emerge, where tiny interactions can be observed with extraordinary clarity. Each new descent into colder territory expands the range of possible experiments and technologies. Each new coldest place becomes less an ending than a platform. That is worth remembering because there is a temptation, whenever science approaches a grand limit, to think only in terms of conquest. Did we get there or not? Did we break the record or not? Did we reach the bottom or not? But the real story is subtler and much more interesting. The coldest places we have ever made are achievements of approach. They exist in the narrow and fertile space between the ordinary thermal world and the unreachable absolute limit. That space turns out to be rich enough to contain superconductivity, superfluidity, condensates, quantum devices, and entirely new ways of probing matter. So when you picture the coldest human-made environments, perhaps it is best not to imagine a giant frozen hall or a cosmic snowstorm trapped in metal walls. Better to imagine a tiny protected region in the heart of a careful machine, deep inside nested shields and vacuum, where atoms or electrons or a small material sample have been persuaded into a level of quiet almost no natural setting provides. A place where every stray source of heat has been fought off with ingenuity. A place where thermal noise has fallen low enough for the universe to begin speaking in a more delicate voice. And once you have that image in mind, the final step in the story almost suggests itself. Because after all these records, all these machines, all these tiny realms of extraordinary cold, the same fact remains. However close we come, the limit still stays ahead. The coldest places we have ever made are not proof that the boundary is yielding. They are proof that the boundary is real, and that the territory just above it is one of the most interesting places science has ever learned to visit. Which means the only thing left now is to stand at that edge and ask what it means that perfect cold always remains just beyond reach, forever defining the journey without ever becoming the destination itself. So we arrive at the edge of perfect cold, and it turns out to be a very unusual sort of edge. Not the edge of a cliff where the ground simply stops. Not the edge of a room with a wall you can touch. Not even the edge of a map where the old cartographers might have written something dramatic about monsters and then gone home feeling pleased with themselves. This edge is real, but it behaves more like a horizon. It is there. It shapes the whole landscape. It tells you which direction you're travelling. It changes the meaning of every step you take toward it. And yet no matter how steadily you move, it remains ahead. That is one of the reasons absolute zero has such a hold on the imagination. It is not just the coldest possible temperature. It is the coldest possible temperature that cannot be completed as an achievement. Physics gives us the number. Thermodynamics gives us the limit. Quantum mechanics tells us that even the imagined endpoint is not the simple perfect stillness our common sense wanted. And human ingenuity, rather than being discouraged by any of this, responds in the most human way possible by building lasers, cryogenic machines, vacuum chambers, and magnetic traps to see how close we can get anyway. There is something almost touching in that. The universe says there is a boundary. Humans reply that they would still like to inspect the boundary from a very close distance, thank you very much. By now, we can see why the limit stays ahead from several directions at once. At the most practical level, every cooling method becomes less efficient as the temperature falls. Heat leaks in through channels that become harder and harder to suppress. Tiny disturbances matter more. The environment becomes less forgiving. The system becomes more delicate. The easy thermal energy has already been removed, so what remains is not a large obvious surplus waiting to be carried away. It is the final faint residue, hidden in the increasingly subtle behaviour of the system. Then there is entropy, quiet and stubborn as ever. Cooling is not merely the removal of energy, it is the narrowing of the accessible microscopic spread of states. As the temperature drops, the range of thermally active possibilities shrinks. Order, in the thermodynamic sense, becomes more demanding. Each further reduction asks for cleaner control, more reversibility, and less waste. Real processes cannot provide perfection. They create a little entropy here, lose a little ideality there, and the endpoint recedes again. And beneath both of those lies the third law, which gives the chase its formal shape. No finite sequence of physical operations can bring a system all the way to absolute zero. That is not a complaint from the laboratory. It is not the bitter diary entry of a very tired cryogenic engineer. It is part of the architecture of thermodynamics itself. However you try to descend, if your procedure consists of real finite steps carried out by real physical means, the last step remains unavailable. Then, almost as if that were not enough, quantum mechanics adds its own refinement. Even if you picture the system as close to the limit as the laws allow, the dream of perfect classical stillness still does not survive. Bound matter retains ground state structure. Residual motion of a quantum kind remains. The world at the bottom is not a silent statue. It is a minimum, yes, but a minimum with fluctuation still written into it. So the edge stays ahead because every layer of the theory agrees that it should. Engineering says the path becomes more difficult. Thermodynamics says the endpoint cannot be attained by finite means. Quantum mechanics says the imagined finish line was never quite what classical intuition thought it was. All the roads point in the same direction. Approach, but do not arrive. There is a lovely intellectual symmetry in that. Early in the story, cold feels very familiar. It is weather, ice, winter breath, a chilled glass, a room that makes you reconsider your choices about clothing. Then physics begins its slow transformation of the idea. Cold becomes less thermal agitation. Temperature becomes a statistical measure of microscopic motion. Absolute zero becomes the lower limit of thermal temperature, and by the time we reach the end, the familiar everyday notion of cold has expanded into something much deeper and much stranger. The coldest possible state is no longer simply the opposite of warmth. It is a boundary condition on the behaviour of matter itself. That is perhaps why the phrase perfect cold sounds so compelling, even though nature refuses to hand it over. It sounds clean. It sounds complete. It sounds like one of those things that ought to exist in exactly the way the words suggest. But science often teaches us that the cleanest sounding ideas become the subtlest under close inspection. Perfect vacuum turns out to be more complicated than emptiness. Perfect stillness turns out to be more complicated than rest. Perfect cold turns out to be more complicated than simply not warm. The closer we get to the ideal, the more the ideal dissolves into structure. There is also something revealing in the fact that the final limit is unreachable, yet everything near it is so scientifically rich. If the world merely became duller and emptier as temperature fell, then the story might end in a slightly disappointing way. But it does not. Near the edge of perfect cold, matter becomes more revealing, not less. Superconductors carry current without resistance. Superfluids flow with astonishing elegance. Atomic gases enter coherent quantum states. Tiny interactions become visible. Noise falls away and the hidden architecture of matter begins to show itself more clearly. In other words, the horizon may stay ahead, but the territory near the horizon is extraordinary. That fact changes the emotional meaning of the limit. An unreachable boundary can sound frustrating if all you care about is possession. If the only satisfying outcome is to plant a flag exactly on the endpoint, then yes, absolute zero is a disappointment. But science is usually at its best when it stops thinking in terms of possession and starts thinking in terms of revelation. What does the approach teach us? What behaviours appear near the limit? What hidden patterns emerge when the familiar clutter is stripped away? In that sense, absolute zero is not a denied prize so much as a guiding principle. It tells us where the interesting terrain begins, and perhaps this is true more broadly than just in low-temperature physics. Some of the most powerful ideas in science are boundaries that organise understanding without becoming ordinary destinations. You do not need to reach a singularity to learn from gravity. You do not need to exceed the speed of light to understand relativity. You do not need to touch absolute zero to discover what matter does when thermal agitation almost disappears. The limit remains ahead, but it is productive precisely because it stays there, forcing every real system to reveal how it behaves under approach, rather than completion. There is also a philosophical lesson here, though physics itself does not require us to become dramatic about it. Human beings often imagine knowledge as conquest. We discover, we master, we reach, we solve. There is some truth in that. Science has changed the world by understanding it deeply enough to act within it. But the story of absolute zero offers a slightly gentler version of scientific success. Here, success does not mean breaking the limit. It means learning why the limit exists, how close it can be approached, and what the world looks like near its edge. We do not own the horizon, we understand it. That is a mature kind of victory, and perhaps a more interesting one. It is the difference between taking something apart and learning how to live intelligently with its structure. The laws of thermodynamics are not obstacles to be outwitted once and for all. They are part of the grammar of reality. The aim is not to bully reality into abandoning its grammar. The aim is to become fluent enough to say something beautiful within it. Low-temperature physics has done exactly that. It has taken an unreachable lower bound and turned it into one of the most fertile scientific frontiers we have. It has shown that impossibility need not mean sterility. It has shown that the final fraction of a degree above zero can contain worlds of new behaviour. It has also shown that human invention thrives under constraint. Give researchers an unattainable endpoint, and they will not simply sulk about it. They will build better instruments, more delicate methods, quieter environments, and stranger experiments until the space just above the forbidden line becomes one of the best understood and most surprising territories in modern science. There is a certain humour in that too. The universe says no final step. Humanity replies that this is fine because the penultimate steps are proving very interesting indeed. Still, it is worth asking what we really mean by saying the edge of perfect cold always stays ahead. We do not mean that the laws are vague, quite the opposite. The limit is well defined. 0 Kelvin is not a fuzzy metaphor. It is the lower bound of thermodynamic temperature. We also do not mean that progress is an illusion. Scientists have genuinely reached temperatures unimaginably close to that bound. Those achievements are not symbolic. They are real, measured, and technologically profound. What we mean is that every real descent remains asymptotic. No matter how impressive the apparatus, no matter how low the number, the final completion still belongs to the category of limits rather than attained states. That word asymptotic is a wonderfully useful one, even if it rarely appears in everyday conversation outside of mathematics, and perhaps a very niche dinner party. It describes a process that approaches a value indefinitely without actually reaching it, and that is exactly the feel of absolute zero. The path bends toward it, the numbers fall toward it, the techniques sharpen toward it. The physics becomes more and more influenced by it, but the destination itself does not become a place where the journey simply ends and everyone packs up the laboratory equipment and goes for lunch. This is important because it protects us from a common misunderstanding. Sometimes people think that an unreachable limit must be somehow unreal, as though reality belongs only to things that can be occupied in a straightforward way. But the edge of perfect cold is real precisely because it governs what can happen nearby. It structures the behaviour of heat capacity, entropy, and low temperature phases. It determines what cooling methods can and cannot achieve. It gives the Kelvin scale its meaning. It shapes the ambitions of whole scientific fields. A horizon can be real without being inhabitable. And perhaps that is one reason the idea lingers in the mind after the technical details settle. Absolute zero is one of those rare concepts that is both scientifically precise and emotionally resonant. It speaks to something very old in us, the desire to find the floor of things, the final boundary, the last possible step. We want to know where the world runs out. We want to know whether there is a bottom to cold in the same way we ask whether there is a beginning to time or an edge to the universe. These are not childish questions. They are the natural questions of a species that keeps finding itself in a lawful cosmos and wanting to know where the laws become deepest. The answer here is that the bottom exists, but it is not a resting place. That may sound disappointing at first, but there is a subtle comfort in it. Reality is not arranged as a series of simple endpoints waiting to be collected. It is arranged as a network of relations, limits, structures, and behaviours. To understand it is not always to arrive somewhere final. Often it is to see more clearly why the finality we imagined was too simple. This is especially true when you remember how the whole story began, with the ordinary sensation of cold. A chilly room, a winter evening, the familiar experience of heat leaving the body faster than comfort would prefer. Nothing in that experience prepares us for the idea that cold will eventually lead to entropy, quantum ground states, dilution refrigerators, laser-cooled atoms, and an unreachable thermodynamic horizon. And yet it does. That is one of the quiet pleasures of physics. It begins with the obvious and ends with the astonishing, then calmly explains that the astonishing was present all along in the obvious if only we had looked closely enough. You can even see this in the way the subject changes our perception of ordinary life. A warm cup on a table is no longer just a warm cup. It is a region of heightened microscopic agitation gradually surrendering energy to its surroundings. A cold window pane in winter is not merely an unpleasant surprise for your fingertips. It is matter with lower average thermal excitation, drawing heat from you because the entropy accounting favours that exchange. A block of ice is not still in the deepest sense. Its atoms still vibrate. Its structure still hosts motion. The whole familiar thermal world becomes richer once you know that absolute zero exists beneath it. As the lower bound, all these ordinary temperatures remain above, and of course that lower bound is not just conceptually beneath them, it is enormously beneath them. Everyday life takes place very far from the edge of perfect cold. That too is worth remembering. We are creatures of the middle range, adapted to a world where thermal energy is abundant enough for chemistry, biology, and weather to thrive. The fact that the laws even permit us to approach absolute zero as closely as we do is extraordinary. The fact that the final step remains unavailable is not a flaw in the universe. It is part of what gives the universe its coherent structure. There is one more thought that belongs here, and it has to do with why boundaries can be so scientifically beautiful. A good boundary does not merely stop you, it reveals the shape of the possible. The shoreline tells you what counts as land and sea. The speed of a light tells you how motion and causality fit together. Absolute zero tells you how thermal behaviour, entropy, and quantum structure fit together. The reason it always stays ahead is the same reason it is so informative. It is not just where the scale ends, it is where multiple deep principles agree on how the world must be. So perhaps the right feeling to take from all this is not frustration but appreciation. The universe allows us to approach deep truths without always allowing us to collapse them into simple possessions. It lets us study the edge of perfect cold with extraordinary precision, create environments colder than most of space, reveal hidden phases of matter, and learn why the endpoint remains forbidden. That is not stinginess. That is generosity of a different kind. Reality gives us the limit and the long approach to it, and in that approach it gives us more science than a fully reached endpoint might ever have offered. If absolute zero could simply be reached and occupied like the bottom floor of a building, the story might actually be poorer. It would be one more thing attained and catalogued. Instead it remains a horizon, and horizons have a way of keeping curiosity alive. They invite movement, refinement, patience, and imagination. They refuse the laziness of finality. They ask not have you arrived, but what have you learned on the way here? And that may be the gentlest way to understand why the edge of perfect cold always stays ahead. It stays ahead because the laws of thermodynamics demand unattainability, because entropy resists perfect reduction through finite means, because quantum mechanics denies perfect classical stillness, and because the universe is built with limits that shape understanding without surrendering themselves as ordinary destinations. It stays ahead not to mock us, but to define the path. And in following that path step by step, degree by degree, fraction by fraction, we end up learning not only what cold is, but what matter is, what temperature means, what order costs, and how deeply the laws of nature are woven into even the quietest corners of reality. So the next time you hear the phrase absolute zero, it may no longer sound like just a dramatic number at the bottom of a thermometer. It may sound more like what it really is: a real boundary, an unreachable floor, a guide to some of the strangest and most beautiful physics we know, the coldest limit in nature, always present, always defining the journey, and always just quietly still ahead.